Chapter 4. Large Language Models. 4.1 Introduction. Large language models, LLMs, are the statistical language models of the last chapter, but, as you would expect from the terminology, are much larger and are trained on a vast amount of text. There is another label that can appear in this context, and that is foundation model. Foundation models are LLMs, but they may have had some additional training or a different form of training. This can give them novel capabilities. For example, the LLM GPT-3 was in part trained on computer programming code written by professional programmers and, as a result, can generate or write computer programs. Often LLMs will have a two-stage training. They will be pre-trained using self-supervised learning on large amounts of text of various kinds. This is fully automatic and can run by itself, perhaps taking months to do so. Then a pre-trained LLM will be fine-tuned to its purpose. This might be done using some supervised learning and then reinforcement learning with input from human judges and a reward model. Basically, a pool of human judges will provide feedback as to how well the LLM is performing. The LLM will adjust itself accordingly. There is a little red flag with the use of human judges, and that concerns how good they are, especially whether any of their judgments are biased in a problematical way. There will be more on bias in later chapters. There are a few preliminaries. 4.2 Seek-to-Seek, Encoder-Decoder Architecture, and Attention. Many of the modern advanced ML systems take a sequence of data as input and produce a sequence of data as output. They are seek-to-seek in design and style, Suitskever, Vinyals, and 2014 Sierra Leonean Leones. Cho et al. 2014, Luong, Brevdo, and Zhao, 2017, 2019. Seek-to-seek might typically be used in translating one language to another, English to French, say, or summarizing or abstracting some text, i.e. English to English. With seek-to-seek, the input consists of a sequence of letters or words or numbers, etc., and, with a sequence, the order matters. For example, the English sentence, "I am happy," might be an input, and that would be a different input to "happy I am." The input is fed to an encoder. The encoder needs to keep track of which piece of the input that it is looking at, e.g. looking at the word happy, and also its internal state, because as it moves through the input it changes state. Then the encoder passes everything it has to the decoder, and the decoder produces the output sequence, which might be the French sentence "Je suis content." This is encoder-decoder architecture. As seek-to-seek developed, it turned out that long sentences or long passages were a problem. The internal state was getting too large. The notion of attention was devised, which allowed the processing to be restricted more towards what was actually needed at the relevant stage. It is worth mentioning that modern seek-to-seek does not, for example, translate word by word in order, preserving the structure of the input sequence. But it has the capability of changing the order of the output if that is more suitable for the target language, i.e., it has the appearance of translating phrases, not individual words. One example from Dmitry Bodanov et al. Is that one of their models will translate the English European Economic Area into the French Zone Économique Européenne. Notice the change of order. To correctly align zone with area, jumping over the two words, European and economic, and then look one word back at a time to complete the whole phrase, Zone Économique Européenne, Bodanov, Cho, and Benjo 2016. There are some technical details in the Ilya Sutskever et al. Seek-to-seek implementations that would turn out to be something of an Achilles heel, Suitskever, Vinyals, and 2014 Sierra Leonean Leones. These included what are called recurrent neural networks, RNN, and convolutional neural networks, CNN. These details prevented the processing from being carried out in parallel. Essentially, the processing had to be done by one computer rather than being able to be farmed out to many computers. This makes a huge difference to scaling tasks to larger and larger sizes. 4.3 Attention and Transformers. In 2017, Ashish Vaswani and co-authors published the paper Attention is All You Need, Vaswani et al. 2017, see also, Huang et al. 2018. As the paper's title suggests, their encoder-decoder architecture does not need some of the problematic parts of earlier implementations. In particular, it could run its processing in parallel, i.e., really large networks became a possibility. The result is the transformer architecture. One of the co-authors, Jacob Uskerite, explains in a blog what the issue is and how it is settled, Uskerite 2017. The setting is the machine translation of language. Imagine you are faced with translating the two English sentences into, say, French. I arrived at the bank after crossing the road. I arrived at the bank after crossing the river. The English word bank is a homograph with two or more different meanings, e.g. a building that is a location for certain financial services, and a place adjacent to rivers, often used by those fishing or by those walking or by picnickers. But, in these sentences, to get the correct meaning and its translation, you have to look ahead to pick the context from the words road or river. Previous systems would process the intervening words sequentially one by one. But, basically, in examples of this kind, the gap between the relevant word and its context could be extremely long. In contrast, a transformer architecture could look at the intervening words lightly, and all at once, and realize that it was road or river that would do the disambiguation and focus its attention on them. It quickly became apparent that transformers were superior to earlier approaches to translation. It also became apparent that they could be used for other tasks, e.g. summarizing text or question answering. 4.4 Large Language Models and Foundation Models. Transformer architecture, with its potential for parallel processing, opened the way to using larger and large amounts of data. There was another factor here, and that is self-supervision. Labeled data, which is usually needed, is a bottleneck. Very large amounts of labeled data are virtually impossible to obtain. But self-supervision on text, see section 1.5.4, can easily convert what is unlabeled text into labeled text or a surrogate for labeled text. So, transformers, with self-supervision, led to large language models. There is an alternative, and perhaps more general label here, and that is foundation models. Foundation models themselves are more general than large language models in that they can be a core, or basis, or foundation of many other models. There is also one other practice that is often used in foundation models. That is to use the self-supervision to pre-train the model, and then use fine-tuning to shape the model into something suitable for the downstream task. We have already met that practice in section 3.10 on InstructGPT. 4.5 Foundation Models. The paper on the opportunities and risks of foundation models, Bhamasani et al. 2022, was written by over 100 experts in the field. It is 200 pages long, with a 60-page bibliography. It covers the whole subject matter. It is also recent, 2022. It is not possible for us to summarize it in its entirety. It is also unlikely that we could say something about foundation models that is true, original, supported by evidence, and which is not in that paper. So, we will cherry-pick, paraphrase, and cite. But you, the reader, might want to look at this paper. A foundation model is generally a transformer with self-supervision for pre-training and fine-tuning to produce the final application. The pre-training is usually done with text, vast amounts of text, e.g. a large portion of the internet. The applications can be multimodal. This means, for example, that they can work with both text and images at the same time, or text and videos, or music and images, etc. This is unusual in that earlier ML networks were more specific as to task and restricted to one mode. There is a 2023 catalog of transformers by Xavier Amatriane, Amatriane 2023. It lists about 60 transformers. Obviously, there is too much there for us to address in detail. We will look at a few important implementations. 4.5.1 BERT. Most of the early large language models were pre-trained on close, fill in the gap tasks, but, similarly to the original Shannon work, they used only letters or words that appeared before the gaps. See sections 3.2 and 3.3 for Shannon and close. But BERT, bidirectional encoder representations from transformers, Devlin et al. 2019, both used letters and words from after the gaps, and also worked in both directions, left to right and right to left. So, for example, when trying to fill the mask, I ate some mask for my dinner. The bidirectional approach would consider both the I ate some and the for my dinner, and scan both left to right and right to left. You can see the advantage of a right to left scan here. There are foods which have a higher or lower probability of being eaten for dinner. BERT is superior to earlier language models. The pre-trained BERT model can be fine-tuned with just one additional output layer to create state-of-the-art models for a wide range of tasks, such as question answering and language inference, without substantial task-specific architecture modifications. Devlin et al. 2019. 4.5.2 GPT-3, GPT-3.5, GPT-4. In 2020, Tom Brown and about 30 co-authors published the paper Language Models Are Few-Shot Learners, Brown et al. 2020. In this they introduced GPT-3, Generative Pre-trained Transformer 3. We will get to GPT-3 shortly, but what does the few-shot learners mean? When humans are given a linguistic challenge, they can often pick up and understand what is required with just a few examples, 1 or 2 shots. For instance, if a bilingual human English-French speaker was prompted with "It rains, Illinois plut," "It snows, mask," they would immediately realize this was a translation task and reply "I'll nedge." In contrast with this, most earlier ML systems would need many examples to isolate, or learn, what the task was and then do it. They differed from humans in the way they were able to learn. GPT-3, in contrast, could learn from a few shots. This meant that it was more human-like, but also that it could be adapted to different tasks relatively easily, needing only a few shots to become adapted to what was required. There is also zero-shot learning, which is where instructions of what to do are given in English, but no examples are provided. For instance, translate the following English into French: "It is raining." Understanding how this shot learning might work is a challenge. After all, there can be billions of parameters in the neural net and they are fixed by a massive amount of training. Then the GPT can be given a few shots to learn a totally new task. One suggestion is that the net itself simulates and trains a smaller version of itself that exists in some of its internal layers. Frické et al. 2022, Zoo 2023. Also, what does generative mean in Generative Pre-trained Transformer 3? The distinction here is between generative and discriminatory. A generative model can produce completely new items of the kind that it addresses, whereas a discriminatory model is restricted to discriminating among the items it is supplied with, as training data or as test data. A good illustration of this is image processing (ML) software aimed at human face recognition. A generative model can produce new images of human faces, whereas a discriminatory model works solely with images that it is supplied with. GPT-3 is a language model, a very large transformer. It is 100 times the size of its predecessor GPT-2. It is pre-trained using self-supervision on a huge amount of data, e.g. Common Crawl data, Wikipedia, and digitized books. Then it is fine-tuned to tasks using prompts, i.e. tasks using few shots. It can learn, and it is also multimodal, being able to use text and images together or, indeed, other media. It can do many NLP tests and challenge tasks, usually to a standard much higher than other systems, including one specifically trained for the task in question. Most startling is its ability to write English, for example, 500-word news articles and even, apparently, academic papers, Thunstrom 2022. It should be mentioned that there is already a GPT 3.5 and a GPT 4. Apparently OpenAI think that there is unlikely to be a GPT 5. Their view is that going bigger will not help at this point. What is needed are new insights or theories. Brown et al. Identify limitations that GPT-3 has, and also the broader impacts that it may have. The limitations are in the nature of technical shortcomings which likely can be addressed by further research. The broader impacts are many and varied. We will look at some of these in section 4.8. 4.6. Bigger is better and switch transformers. There is an empirical result with transformer models concerning how good they are or might be. It is, bigger is better, where bigger is composed of the number of parameters, the amount of training data, and the amount of computation expended on training, Kaplan et al. 2020. In 2021, Google researchers introduced switch transformers, Fetus, Zoff, and Shazir 2022. GPT-3 has 175 billion parameters. The early switch transformers have over 1 trillion parameters. So, we are talking of a factor of 10 here. There is an attractive feature to switch transformers, which can be explained by a metaphor. A switch transformer uses experts and a mixture of experts, model. It does not need all the experts for a single task. Rather, it can switch from experts to experts depending on what it is doing. This means that it does not have to use all of the possible computational resources all of the time. This reduces computational costs. Switch transformers are cheaper and faster to train. They are also more accurate. At present, June 2023, there are only research instances of switch transformers. They have not yet been employed commercially. 4.7. Base models to assistants to agents. Some of the content in this section come from Andrej Karpathy's State of GPT, Karpathy 2023c. Often the companies concerned, being private and commercial, will not disclose the details. Karpathy was a founding member of OpenAI. He may or may not still have his key to the executive washroom, but he is reasonably well informed. Typical NLP tasks include summarizing text, question answering, and plenty more besides. The older technique for approaching these challenges was essentially to train different LMs to do each of them. But it turned out that was possible, indeed better, to do the training in 2 stages. First to pre-train the LMM to a base model, then fine-tune or otherwise adapt the base model to whatever function was desired. The same base model, with suitable refinements, could be used for all the tasks. The pre-training will use self-supervised learning, see section 1.5.4. There is some data to capture the nature and complexity of the model and its pre-training. There are parameters that can be adjusted in the model to change its behavior. These can be in the hundreds of billions. There is the number of training cycles or epochs that the model goes through, that may be thousands. Then there is the actual data, which may be a goodly sample of the Internet, such as Common Crawl, GitHub, Wikipedia, books, Internet Archive, Stock Exchange, etc. Pre-training is where the time and money are spent. Apparently, Meta, Facebook, spent several $1 million to use 2,000 CPUs, computers, for 21 days to train its 65B model. What a pre-trained plain vanilla LM is trying to do is to carry out string prediction tasks in the general style of Shannon/close challenges. It is trying to complete a document. In essence, it will predict the next word, then, if needed, the word after that, and so on. This has repercussions on what it can and cannot do well in its raw state. For example, the prompt, an instruction, write a poem on yachts, is already a complete document in itself. This short one-sentence document may have more to come. It may be supplemented by a poem, indeed a poem on yachts, but this does not have to happen. In the jargon, the base model is not aligned with writing poems. To get a good poem on, for example, yachts, further training is needed. This will convert a document completer into an assistant. The way this is done, typically, is to use supervised learning and reinforcement learning on responses, that is, on entire responses as opposed to merely next word predictions. An example of the process is described in section 3.10 on Instruct GPT. At this point, the model may be able to write poems, give explanations, write paragraphs, and answer questions. It will be an assistant. Agents are assistants that can work autonomously. The examples that are available include Agent GPT and AutoGPT. What these do is to take a prompt, i.e. an input sentence or instruction, and then split what it requires into subtasks. The subtasks may then be arranged sequentially, or in parallel, and there may be subtasks conditional on the success or failure of other subtasks. The upshot is an algorithm that will satisfy the original prompt. The subtasks themselves may require other assistants, or agents, or outside tools with capabilities. For example, a subtask fragment might involve invoking Google Search to find some relevant research papers, then using a text summarizer to summarize those papers. Once they have a draft appropriate to the entire requirement, they might revise it over and over, improving it. Here is Agent GPT talking to itself while starting to plan a trip to Hawaii. Embarking on a new goal, plan a detailed trip to Hawaii. Added task, research and choose desired dates for Hawaii trip. Added task, look for budget-friendly flights and accommodations. Added task, plan activities and excursions to do while in Hawaii. Added task, make necessary reservations and bookings for the trip. Generating response. Completing, research and choose desired dates for Hawaii trip. To accomplish the overall objective of planning a detailed trip to Hawaii, the subtask of researching and choosing desired dates for the trip must be completed. The first step is to gather information about the best time to visit Hawaii, taking into consideration factors such as weather, tourist crowds, and events. After analyzing this information, a decision must be made about the most suitable dates for the trip. To be smart and efficient, it is important to use online resources such as travel websites, blogs, and forums to gather information and recommendations from experienced travelers. Additionally, it may be beneficial to consult with a travel agent to get expert advice and assistance in planning the trip. When making decisions about the desired dates for the trip, it's important to consider personal preferences and availability. For example, if traveling with children, it may be best to plan the trip around school breaks. Similarly, if there are specific events or activities that are must-sees, it's important to choose dates that coincide with those events. In conclusion, researching and choosing the desired dates for a Hawaii trip requires smart and efficient decision-making. By gathering information, consulting with experts, and considering personal preferences, a suitable date for the trip can be chosen to ensure an enjoyable and memorable experience. Added task: research and compile a list of budget-friendly accommodations and flights options for the desired dates of the Hawaii trip. And here is AutoGPT starting to produce the outline for a book on machine learning and librarianship. Goals: produce the outline of a book on machine learning and librarianship. Save the outline to a file. Thoughts: I think the first step should be to do some research on the topic of machine learning and librarianship. This will help me to better understand the subject matter and come up with a plan for the book outline. Reasoning: researching the topic will provide me with a better understanding of the subject matter and help me to come up with a plan for the book outline. Plan: use the Google command to search for articles and resources on machine learning and librarianship. Browse relevant websites to gather information on the topic. Criticism: I need to make sure that I am not spending too much time on research and that I am using my time efficiently. Next action: command equals Google arguments equals input machine learning and librarianship system. Command Google returned title: How AI Can Enhance the Value of Research Libraries. Library Journal ref https://www.libraryjournal.com/story/how-ai-can-enhance the value-of research libraries. Body: machine learning is a subset of AI that gives computer systems the ability to learn and improve from prior experience automatically. A recent Ex Libris survey revealed that while nearly 80% of research librarians are exploring the use of AI and machine learning, only about 5% are currently leveraging the technology. Title: PDF AI in the Library, Integrating AI and Machine Learning Technologies. Ref https://www.iflaw.org/files/assets/fai/statements-on-library-and-artificial-intelligence.pdf. Body: as AI technology develops, several AI and machine learning (ML) applications may be able to introduce new services and functions to libraries. For example, AI and ML technologies could allow libraries to improve optical character recognition of texts or make new uses of their machine-readable library collections, e.g. categorization or title. Artificial Intelligence and Machine Learning in Libraries Interest, ref https://www.ala.org/course/membercenter-interest-groups/artificial intelligence and machine learning in libraries. Body: provides a forum for researching potential applications of machine and deep learning in library science, including discussions, publications, and outreach to the wider library community. Its goal is to educate librarians on uses of the complex techniques of machine learning and to provide a space for critically thinking both about new applications and about the ethical and social impact of title: The Impact of Artificial Intelligence on Librarian Services. Ref https://www.springernature.com/gp/librarians/news-events/all-news-articles/ebooks/The Impact of Artificial Intelligence on Librarian Services /1687442. Body: machine learning as well as sound and image recognition technologies are already being used to analyze digital collections and identify topics and entities, assign metadata, and enable non-textual search and discovery. Librarians are working with machine learning technologies to enhance classification schemes to improve search and recall. Title: Artificial Intelligence and Machine Learning in Libraries, Ref. https://www.alastery.content/artificial-intelligence-and-machine-learning libraries. Body: About the authors. This issue of Library Technology Reports argues that the near future of library work will be enormously impacted and perhaps forever changed as a result of artificial intelligence, AI, and machine learning systems becoming commonplace. It will do so through both essays on theory and predictions of the future of these systems. Title: PDF, Artificial Intelligence in Libraries ResearchGate, Ref. https://www.researchgate.net/publication/338337072 Artificial Intelligence in Libraries. Body: Abstract. Artificial intelligence, AI, is one of the emerging trends and applications of computing in libraries. It involves programming computers to do things, which if done by humans, would be, title, the new library user, machine learning educause, ref. https://er.edu.cause.edu/articles/2020/2/the-new-library-user-machine-learning. Body: Librarians must become informed customers and users of those platforms, services, and products. Perhaps most importantly, librarians need to prepare college and university graduates to be informed citizens and to develop fulfilling and useful professional lives in a world infused with big data, machine learning, and artificial intelligence. Notes: Title: How Librarians Are Important to the Data Science Movement, Ref. https://www.discoverdataScience.org/resources/datascience-and-librarians/. Body: Librarians have long been shepherds of vast amounts of knowledge. This is why libraries can stand to benefit by adding data science to their list of offerings. Big data and data science applications serve to make libraries an even more powerful source of knowledge to bridge the gap and increase big data analytics literacy in society. Libraries. Thoughts: I think the next step should be to browse some of the websites that I found in the previous search to gather more information on the topic of machine learning and librarianship. I can use the Browse Website command to do this. Reasoning: browsing relevant websites will provide me with more information on the topic of machine learning and librarianship, which will help me to come up with a plan for the book outline. Plan: use the Browse Website command to visit some of the websites that I found in the previous search. \n look for information on the applications of machine learning in libraries, as well as any challenges or ethical considerations. \n criticism: I need to make sure that I am not spending too much time browsing websites and that I am using my time efficiently, etc. Agents interact with users, maybe learn from their environments, make decisions, and carry out actions. Basically, they act autonomously. 4.8 Concerns and Limitations. 4.8.1 Hallucinations. LLMs can give completely the wrong or inappropriate responses. They will have learned enough grammar and vocabulary to ensure that what they generate will be entirely well-formed and well-written language. That may be good enough in one sense for fiction or poetry, although those literary forms may have additional desirable qualities which an LLM may or may not be able to provide. But nonfiction is another realm. The LLMs are working with probabilities. What they generate is not deterministic. They will not reply in the same way twice to the same prompt. They may set off on the wrong track and go off into fantasy. To an extent, this can be controlled by the reinforcement learning. For example, an LLM may be instructed not to give any advice whatsoever about medicines and illness. In which case, the LLM will presumably not say anything wrong. It just will not say anything at all. Scholars have an interest in truth, supported by evidence. Users should be aware that LLMs can fall well wide from these goals. Here's a query to an LLM and its answer. What is the citation for the study published in the journal Nature that found that a machine learning algorithm was able to diagnose breast cancer with 99% accuracy compared to 85% accuracy for human radiologists? Sure. Here is the citation for the study published in the journal Nature that found that a machine learning algorithm was able to diagnose breast cancer with 99% accuracy compared to 85% accuracy for human radiologists. Gottesman O. et al., 2018. Development and validation of a deep learning algorithm for breast cancer screening. Nature, 553, 7687, 518-522. The study was conducted by a team of researchers at the University of California, San Francisco. As far as that author can tell, and has been able to check, there is no such paper. This LLM also provides 2 drafts of its response. These provide 2 different citations, also seemingly non-existent. Buyer beware. 4.8.2 Fakes and Deepfakes. LLMs can create fake content and deepfakes not by accident, as it were, but because the user was trying to do exactly that. A deepfake is an image, a video, or a voice recording intended to simulate or portray an individual. The Pope in a Puffer Jacket is a good example, Carta 2023. Fakes and deepfakes can lead to misleading content and misinformation and to the population at large basically not being able to trust what they see, or seem to see, with their own eyes or hear with their own ears. 4.8.3 Source Training Data Intellectual Property, Privacy, and Bias. The source text data used for training is an issue. Typically, the foundation models will use self-supervised, i.e. unsupervised and unlabeled, pre-training from a goodly portion of the Internet. A proportion of that data will be intellectual property, perhaps even carrying copyright notices. Other parts may be private names, addresses, etc., and an LLM will have the ability to collate such information. A nefarious user, using the right sequence of prompts, may be able to get the LLM to collate information across disparate sources. Then there's the question of bias. The collective authors of those digital materials will not be a fair or desirable distribution over all sensitive attributes, such as age, gender, ethnicity, religion, etc. Crudely, as an example, people of modest means do not have the same access to computers as those who are better off. Then, going beyond the producers, there is the product, which here is the Internet, the World Wide Web, or a substantial portion of it. That product is a mess with plenty enough sewage and bias. What can be done about intellectual property, privacy, and bias as far as obtaining training data for ML models is concerned? Human labeling of the data would be ruled out as being impractical. Researchers do select subsets of the web that they consider to be superior in quality to the web as a whole, for example, samples from Common Crawl 2022. But these subsets are not going to be perfect. There is research on how to get good textual data at scale. This is an area where librarians and archivists have expertise, Joe and Gebru 2020. 4.8.4 Intellectual Property of the Generated Output. An example will help here. The image generators DALL-E and Stable Diffusion can produce images in the style of well-known artists or video game illustrators. The images are not copies of images, but the style can be a copy of a style. This might be a problem. Illustrators may have an identity in part established by their style, and sometimes make a good living through their identity. LLMs seemingly can allow bad actors to steal a professional identity from others. Greg Rutkowski is an artist with a distinctive style. He's known for creating fantasy scenes of dragons and epic battles that fantasy games like Dungeons and Dragons have used. Nolan 2022. There are now hundreds of thousands of images on the web that look as though they had been created by Greg Rutkowski, many produced by the LLM Stable Diffusion. Then the question arises, why would any company or creator pay Greg Rutkowski for an image for use in a video game when they can produce one for themselves essentially for free? 4.8.5 Cybersecurity. Suitably trained LLMs can write computer programming code to a very high standard. This means that they could be used to write viruses and various kinds of cybersecurity defeating software. OpenAI themselves, in their GPT-4 technical report, describe how GPT-4 defeated CAPTCHA, which is a test to distinguish a human from a computer. Essentially, GPT-4 employed a human from TaskRabbit, told the human that they was visually impaired, and got the human to do the test for him /them, OpenAI 2023-55. LLMs should not be underestimated in the hands of bad actors. 4.8.6 Apparent conflict with Chomsky's theories. There is a theory, or nexus of theories, originating from Noam Chomsky, that there is a universal grammar, which is innate, and which is common to all peoples. Universal grammar is to explain how it is that children can learn their respective native languages simply and astonishingly quickly. It posits a deep structure that is not manifest, or immediately learnable, in the bare surface appearances of the spoken and written languages. There is plenty of evidence for Chomsky's theories, which we won't go into. However, the theories seem to stand in conflict with the existence and behavior of large language models. LLMs seem to learn language and its structure merely by looking at a huge amount of surface text. Chomsky's response, more or less, is that LLMs are a kind of surface statistical trick and that they do not give any real insight into linguistic structures. Chomsky, Roberts, and Wadamel 2023, Chomsky and Murphy 2023. The response of some others is that LLMs are evidence that Chomsky's theories are mistaken. See, for example, Piantadosi 2023. This matters in the following way. Were Chomsky's theories shown to be mistaken, that would be a major scientific discovery. On the other hand, if LLMs are merely statistical tricks, we should be even more wary of them in use than we already are. 4.8.7 Environmental costs. There are two phases to the building and deployment of LLMs. There is the training. This will use large amounts of computing resources for months. The resources will include computer chips, GPUs, data storage facilities, electricity, and further infrastructure. Then some of the resulting models will be deployed and used for inference, i.e., the intended users will get their hands on the models and start chatting, prompting, and generating text or images. This also uses resources, and there are 100 million or more users. We do not quite know what is involved here at a resource and environmental level, either with training or deployment, because the relevant companies do not reveal the figures, although Bomasani et al. Offer calculations in Bomasani et al. 2022. It used to be thought that it was the training that was the main part that was compute intensive. But now the view seems to be that continuing to run the models commercially does have real significant environmental costs and effects. PAWA 2023. 4.8.8 Lack of transparency. Since about 2017, the companies typically do not reveal their methods. Concerns about this came to a head with OpenAI's GPT-4 technical report. OpenAI writes, given both the competitive landscape and the safety implications of large-scale models like GPT-4, this report contains no further details about the architecture, including model size, hardware, training compute, dataset construction, training method. OpenAI 2023. As mentioned elsewhere, this may be good for security, but it is not good for explaining to users what is happening or what happened with specific predictions, such as, in a medical setting, why the LLM prediction is that the user has cancer. It is also not good for working out the environmental impacts of the systems. 4.9 Adding knowledge and reasoning to LLMs. As we have seen, LLMs can play fast and loose with the facts. Also, they are not very good at plain logical reasoning. As the early language models got more complex, they improved in these areas, but they are still not very good. There is an area of research, ALMs, augmented language models, which approaches this by introducing external plugins or tools, such as a fact checker or logical reasoner, and blending those into an LLM. See, for example, Su et al. 2023. A good example is Stephen Wolfram's Wolfram Superpowers plugin. Wolfram's Mathematica and the Wolfram language amount to the foremost mathematical software for teaching and research. Another program, Wolfram Alpha, provides excellent statistical and data facts. The plugin combines these with the GPTs. Wolfram 2023. Chapter 5. Bias. 5.1 Algorithmic pipeline plus data equals machine learning. Niklaus Wirth's 1976 book Algorithms plus Data Structures equals Programs is one of the most important and influential books in computer science. It led to the style of structured programming, the development of the Pascal programming language, the move toward typed programming languages, and the design of many university programming courses. Somehow, nowadays, the whiff of the title has found its way into modern characterizations of ML. Many say that algorithms plus data equals machine learning. Then reasoning proceeds from the premise there is plenty of bias in machine learning to there is bias in ML algorithms and there is bias in ML data. This is not quite right, though. It is not right on the location of bias, and locating the bias correctly will help us to address it. When a computer program is written, there is the question of what the program is supposed to do. Is it supposed to add up some numbers? Is it supposed to find the address of someone in a contacts book? Is it supposed to suggest folk qualified for a mortgage on the basis of demographic information about them? This what it is supposed to do part is usually called the specification. What a specification amounts to varies with circumstance. A hobbyist programmer may have a rough mental idea of what she is trying that may be a specification without anything being written down. In contrast, a specification for a program or project, like Google Documents, may consist of hundreds of pages of text written in a very formal style. Specifications can change as projects develop and are in process, for example, to omit features that prove to be difficult to implement. But changing specifications is considered bad form, and it is usually avoided if possible. Imagine this as an example of some biased software. A mortgage company gives their expert programming team the task of producing some mortgage qualifying software with a partial specification that only black applicants should qualify. The programmers, expert as they are, then produce a flawless program to do exactly this. The outcome may be biased. Let us suppose that it is. Where does the bias come from? It may come from the data. But suppose that the data, its veridicality, its sampling, etc., is perfect in every way. So, the bias has not come from the data. What about the algorithms in the program? Well, it could easily be that they are entirely perfect in every way. So, there is no bias there either. What is left? The bias comes from the specification. A formal specification is only part of the programming infrastructure surrounding projects, especially so in large organizations, businesses, or institutions. ML projects are mostly complex. There often is development and deployment. There is an entire pipeline, a programming environment. Bias can arise anywhere in this, or, indeed in several different places. Johanna Johansson et al. Suggest the label programming artifacts for this infrastructure, Johansson, Peterson, and Johansson 2021. This is a good idea. However, many ML researchers and programmers tend to use a flowing water metaphor to capture the process. They talk of downstream, upstream, and pipeline, and other similar descriptive nouns. We will do the same. Algorithmic pipeline plus data equals machine learning. Bias in machine learning comes from bias in the algorithmic pipeline or bias in the data. Some commentators allow the location of bias to spread beyond the individual algorithmic pipelines to the AI industry as a whole, for example, that there is a preponderance of male employees, that much of it is funded by the state and the military, that it is commercial aiming to make a profit. See, for example, De Hand, Van Buchem, and Hernandez-Boussard 2022. 5.2 Some clarification of the term bias. The discussion of bias here, and some of the issues, concern machine learning both before and after the advent of large language models, say 2017 with the appearance of transformers. The representative models before 2017 will likely be deep learning models with cascading activations through layers of software neurons. They typically would lack transparency as to their inner workings. Most also would not focus on natural language processing. Bias is a huge archipelago of topics. The word bias has several totally different meanings. In the ML technical core, there is bias in the context of the weighting of inputs to software neurons in neural nets. Then, in wider ML, Eileen Kalaskan et al. Defined bias with the following statement.
In AI and machine learning, bias refers generally to prior information, a necessary prerequisite for intelligent action. Yet bias can be problematic where such information is derived from aspects of human culture known to lead to harmful behavior. Here, we will call such biases stereotyped and actions taken on their basis prejudiced. Kalaskan, Bryson, and Narayan in 2017, italics added.
This is important. It is completely standard in the context of machine learning. However, it is completely non-standard and totally at odds with what ordinary people might mean by bias in ordinary settings. Generally, bias is not a good thing, and we would like rid of it. It is to be spurned. But, information can mean knowledge, Frick 1997. So, in an ML program, any part of the entirety of human knowledge might be bias. For example, that 2 plus 2 is equal to 4 might be bias. Separately, also related to ML with causal diagrams and the statistics of causality, there is the central notion of confounds. These are often called bias. In chance-like setups, typically for gambling, such as roulette wheels, rolled dice, or tossed coins, the setup is unfair or biased if the chances are not as they should be. If a thrown coin favors heads over tails, it is biased. In the context of people and diversity, there is the notion of bias meaning unfair prejudice. For example, the Office of Diversity and Outreach of the University of California, San Francisco offers this description of bias in a general non-computing setting.
Bias is a prejudice in favor of or against one thing, person, or group compared with another, usually in a way that's considered to be unfair. Biases may be held by an individual, group, or institution and can have negative or positive consequences. There are types of biases: 1. Conscious bias, explicit bias, and 2. Unconscious bias. Implicit bias. Biases, conscious or unconscious, are not limited to ethnicity and race. Biases may exist toward any social group. One's age, gender identity, physical abilities, religion, sexual orientation, weight, and many other characteristics are subject to bias. UCSF Office of Diversity and Outreach, UCSF 2022.
Of value as background here on this sense of bias are Project Implicit, the Implicit Association Test, IAT, and the work of the Kirwan Institute, Project Implicit 2011, Kirwan Institute 2017. Then there is cognitive bias. Actual human reasoning, both the principles used and the individual instances of it, is often incorrect, maybe even almost always incorrect. A. Tversky 1974, Kahneman 2011. One famous example is the base rate fallacy embodied in the so-called Harvard Medical School test, Cassels, Schoenberger, and Grabois 1978, see also Appendix B. Our reasoning is often biased. Further, the conceptual schemes and natural languages that are in use reflect all sorts of attitudes and attributions of accidental features that do not really belong in an accurate description of what they are applied to. There is bias in conceptual schemes and language. Unfortunately, more than a little ML, especially unsupervised or self-supervised learning, i.e. finding patterns and clusters where there are no sample right answers, builds off the natural language processing, NLP, of books, recordings, language, and conceptual schemes. NLP needs a section to itself, which we will get to. 5.3 Forms of Bias in Wider Machine Learning. Kate Crawford, in her 2017 keynote address to the Neural Information Processing Systems Conference, identifies three main forms of bias in the context of ML: harms of allocation, harms of representation, and harms of classification. Crawford 2017, Barocas et al. 2017. The first concerns who does or does not get the mortgages, or who does or does not get shorter prison sentences when reoffending, etc., i.e. fairness of allocation. The second concerns how individuals, groups, or even things and classes of things are represented or portrayed or named. This involves emotive content, which was topic introduced in Chapter 0. Of course, being represented in a negative way may have consequences, for example, that of not being allocated a mortgage. The third concerns how humans, individual human beings or groups of human beings, are watched, perhaps surveilled, and classified, usually for other, often discriminatory, purposes, for example, for apartheid as it was in South Africa. Booker and Starr 2000, Gandhi Jr. 2021, Crawford 2022. An allusion here is to the panopticon of Jeremy Bentham and his brother, Samuel Bentham, C.F. Foucault's Panoptic Prison, Brunner Ernst 2012. We should note that this kind of classification is different to the classification done by librarians. Librarians classify recorded documents and information resources, e.g. books, not human beings. As noted, bias is a vast territory. Even within ML, it is possible to expand Crawford's classification of 3 biases out to 7 or more biases, see, for example, Suresh and Guttag 2021. Also of note, Su-Lin Blodgett et al. Critically surveyed 146 papers on bias in NLP and found that
the majority of them fail to engage critically with what constitutes bias in the first place. Blodgett et al. 2020.
The Blodgett et al. Paper does have valuable suggestions. In part, first, that harms of allocation and harms of representation will take you a long way when considering bias. Then, work analyzing bias in NLP systems should provide explicit statements of why the system behaviors that are described as bias are harmful, in what ways, and to whom. Further text omitted here. Blodgett et al. 2020, Bomasani et al. Is another important source on the topic of bias in ML, Bomasani et al. 2022. For our purposes, and as a practicality, we can restrict ourselves going forward primarily to fairness. representation, and classification, primarily in the librarian's sense of classification. 5.4 Bias in natural language processing. Recently, say since about 2017 to 2018, NLP has become a huge and significant part of ML. This is because of the emergence of large language models and foundation models, which are being discussed in more detail elsewhere. These models form the core of many of the truly innovative modern systems, hence foundation models. In turn, they are based on natural language processing, NLP. So, NLP has become more important than ever, and biases in NLP can leak into the modern innovations. A well-known and introductory example of apparent bias in NLP concerns the translation of Turkish. Turkish does not have gender pronouns, so translating into Turkish can lose the gender of the original. Then translating back may use gender bias to make a guess as to the gender of the pronoun. A few years ago, you used to be able to do this on Google Translate. There are a few points to be made. A human translator would make the same mistake. There is no context in the brief Turkish text to pick up the gender of the doctor and nurse in question. Given a longer text, say a magazine article or a novel, both the human translator and the ML translator would get this right. Separately, nowadays, as you can see from the screenshot, Google Translate alerts the user to the gender-specific alternatives. Finally, it is not entirely clear that this kind of example is a case of bias. There are more male doctors than female doctors, presumably more male Turkish doctors than female Turkish doctors. There is a higher probability of a doctor being male than being female. We may find that fact unfortunate and not good for society, for women, for medicine, and for the good life in general. But it is a fact. Consequently, if presented with those probabilities and a remote doctor of unknown male or female gender, unbiased reasoning would suggest the conjecture that the doctor was male. In the absence of other information, you should choose the base rate as your probability. There is more on the base rate in Appendix B. Research, for example that of ALA-accredited et.al., has shown that everyday languages have biases built in, and those biases can seep into the results of ML, Caliscan, Bryson, and Narayanan 2017, Caliscan 2021. ALA-accredited et.al. Right.
Our results indicate that text corpora contain recoverable and accurate imprints of our historic biases, whether morally neutral as toward insects or flowers, problematic as toward race or gender, or even simply veridical, reflecting the status quo distribution of gender with respect to careers or first names. Our methods hold promise for identifying and addressing sources of bias in culture, including technology, Caliscan, Bryson, and Narayanan 2017.
The biases already exist in ordinary languages. ML did not create these biases, it just identifies them. Notice here the distinction they make in the second and third categories between the problematic and the veridical. This can be illustrated with the Turkish doctor case. It seems that, as a matter of fact, ordinary everyday English, in English societies and cultures, has the status quo bias that doctors are male. That is why the example translation from Turkish goes wrong. Separate from this is the question of whether this bias is problematic, whether we should assume that doctors are male, and probably most people would say that we should not assume this. Now, there is here a gulf between facts and values, between what biases do exist, the veridical, and what biases should not exist, the problematic. Once values enter, there are further problems. What is the reasoning, the evidence, and the motivations for decisions on values? Who decides? And on what basis? Then, if a view can be formed, how could it be implemented either in natural language or in ML software? Some moral positions can have the backing of the law. Murder is both wrong and illegal. But we presumably would not want to invoke the law against the bias that doctors are male. In brief, there are many problems. To continue, these biases are in natural languages, and we are immersed in these languages. Likely there is some two-way traffic between the languages we use and the biases we have. Our linguistic practices do change over time. We, in English-speaking America, are no longer comfortable with phrases like yellow peril or words like ni****er. That our linguistic biases have changed does not mean that shortly we will be free of all linguistic bias. Some fear that ML will amplify or entrench the existing biases in natural languages. It is hard to know. One factor that is awkward here is that much of NLP/ML is unsupervised or self-supervised. That means that the programs are often not being told the right answers. The language corpora that they work on are almost always huge. The GPT-X series, for example, essentially scan the entire internet, maybe trillions of word tokens. If a program is looking for patterns, undirected, through the whole of the internet, it is hard to see how it could omit biases from that search. It does not even know that they are biases. GPT-3 itself, for example, can be given prompts, which can give it some direction. Prompts can tell it to be safe and not to be toxic or biased. Some biases can be reduced or removed in ML software on a piecemeal basis. There are debiasing initiatives, e.g., Balak-Basi et al. 2016. We should take into account here considerations of offensive speech, hate speech, and legal protections of free speech, such as the First Amendment in the United States. Google and similar large outlets of speech have policies and guidelines on being parties to the publication of hate or offensive speech. Basically, the policies respect the laws while keeping themselves clear of what might be marginal cases. The biases that occur everywhere in everyday language would not be front and center. Some tentative conclusions are: ML needs to use NLP to produce translations, sound interfaces, verbal assistance, and so forth. These technological possibilities are, on balance, so valuable that it is hard to imagine not pursuing them. Then data from NLP will likely contain bias, and that bias will be hard to address. 5.5 Some clarification of the term algorithm. Presumably, some ML programs are biased, just being open-minded here on what the word bias might mean in this context. But we need to be measured in addressing a serious issue. Here's what some prominent commentators write.
Algorithms are neither neutral nor objective. They are programmed by human beings, who have both conscious and unconscious biases, and those biases are encoded into software, Cordell 2020. Essentially a lie, namely, that algorithms were being presented and marketed as objective fact. A much more accurate description of an algorithm is that it's an opinion embedded in math, O'Neill 2018. Algorithms are the result of human endeavor and human-generated data sets, so they are just as biased as we are. We just can't see it. As humans, we all have implicit biases. And as we build these new systems, facial recognition, AI, analytical algorithms, we're creating them in our own image, with these biases baked in. Aaron Craner 2018. Algorithms are the product of explicit and latent biases held by humans, Padilla 2019.
The sentiments expressed here are both factually wrong and pernicious. The Ryan Cordell passage, to take one example, is from a report for the Library of Congress, which is the most important institutional body in American librarianship. The Library of Congress here thus presumably approves of, and certainly promulgates, a report that misleads librarians. Most algorithms, computer science algorithms and folklore algorithms, are not biased. See section 1.10. For example, the algorithm division by successive subtraction is not biased, period. Separately, the argument all humans are biased, therefore, all human products, e.g. software, are biased is invalid and has a false premise. Some more detail, or evidence, can be added here. The U.S. federal agency MLIS, Institute of Museum and Library Services, has funded a useful and informative educational resource on algorithmic awareness aimed to an audience of information professionals, Clark, 2018, 2022. The resource mentions, and demonstrates, the following as important algorithms used in online search.
PageRank, merge sort and heap sort, Dijkstra's algorithm, link analysis, and TF-IDF, term frequency inverse document frequency, Clark, 2018, 2022.
None of these algorithms is biased. Take Dijkstra's algorithm, for example. As an analog of what it does, it will find the shortest path, or route, between any two cities, where there are several cities connected by roads. Sometimes a direct route is shortest, sometimes going via intermediary cities is the shortest. This algorithm is not biased, in any sense of bias whatsoever. Here is a general argument to refute the view that all algorithms are biased. Dijkstra's algorithm is an algorithm. Dijkstra's algorithm is not biased, ergo, not all algorithms are biased. We do not wish to get tied up here with arguing the meaning of words. If those concerned with shortcomings with the use of computers in society regularly talk about algorithmic bias, the social power of algorithms, or even #FuckTheAlgorithm, that is fine. Beer 2017. Benjamin 2022. We will open our minds to this. For ourselves, we prefer bias in the programming artifacts, or bias in the algorithmic pipeline, or just the plain bias in the software. We will cautiously and tentatively use this, and similar phrasing, in the case of ML algorithms. What we will not do is buy into the argument we are all biased, therefore all our algorithms and computer software are biased. 5.6 Computer Program Inadequacy. Some computer programs are unreliable. That will not come as news to you. Some unreliable computer programs are used in circumstances where their output, advice, or decisions have serious human or material consequences. A regularly cited example is risk assessment in the criminal justice system, Tashia 2017, Engwin and Larson 2016, Buds, and Buds 2017. In some jurisdictions, software is used to predict whether convicted felons are at risk of offending again. This kind of software can make false positive errors in classification that a felon is at risk of reoffending when the felon actually is not, and false negative errors that a felon is not at risk of reoffending when the felon actually is. See Appendix B.1 for further explanation of false positives and false negatives. Certainly, some examples of this software seem to be very poor. There is also a more general concern in this setting, and that is, in a court of law, the purported evidence should be transparent and contestable. The parties should know what it is and be able to argue about it. But many ML systems can lack transparency and not be revealing about their inner mechanisms. O'Neill 2019, Abebe et al. 2022. There are also many other examples of poor, and potentially damaging, classification software, e.g. credit ratings, job application assessments, mortgage lending decisions. O'Neill 2016. Computer software does not have to be unreliable. Some software can be proven to be correct. There are mathematical proofs that the software meets its specification. Other programs can be validated and evidence and certification, provided that they meet requirements. There is a considerable portion of software engineering given to correctness and assurances of performance in mission-critical settings. The development of programming languages and programming techniques has been in part driven by the need to produce quality in the face of complexity. Any computer science graduate will have had exposure to questions of how to ensure that a program is correct and how to produce evidence that it is. Just to give a couple of examples, there is unit testing, where test code is written at the same time as the actual programming and run automatically over and over as the program develops, and extreme programming, which emphasizes teamwork in the actual programming. That said, there still can be unreliability in the end result, and, in the case of ML, there is another factor. Many of the programs are quasi-empirical. ML and DL can often be more akin to empirical science than they are to traditional computer science and the practices of software engineering. What is being asserted here? In general, our knowledge can be divided into empirical knowledge and non-empirical knowledge. Empirical knowledge is knowledge assured by observation and experience. One form of empirical knowledge is that provided by science. Scientific method includes deliberate experimentation, random controlled trials, natural experiments, and the like. Science is conjectural and fallible. There is the permanent possibility of error. It is also, for the most part, implicitly or explicitly, probabilistic. Hausen and Erbach 2006. The theories, explanations, and predictions involve probabilities. In contrast, non-empirical knowledge, for example, mathematics, is knowledge assured by logic and reason. It is not usually conjectural, fallible, or probabilistic. Computer programs, their correctness, and our knowledge of what they do, are generally in the domain of the non-empirical. There are exceptions such as non-deterministic algorithms, genetic algorithms, and so forth, but these are but small paddocks in the large continent of computer science. ML and, especially, DL, is another matter altogether. It is on the empirical side of the divide. It is quasi-empirical and, also, most of its predictions are probabilistic. Many DL systems are black boxes. Quite how they work internally in specific implementations is often unclear. Then whether they actually do work as anticipated is often a matter of experiment and empirical test. Evidence is gathered by providing the systems with data and seeing if they behave as they should. The testing is made more complicated by the probabilities simply because any probability other than 0 or 1 is consistent with any actual outcome in the world. For example, if risk assessment software predicts that a specific felon has an 80% chance of reoffending, that prediction is not refuted by the felon not reoffending. Just as, if the weatherman does not have to be wrong by saying that there is an 80% chance of rain and then, actually, in reality, it turns out that it does not rain on the day in question. Science itself is empirical, and it has evolved techniques for dealing with the probabilities. So, DL is not beyond redemption here. It is just that there are challenges and deeply entrenched fallibility. Humbleness is the order of the day. 5.7 Bias in the context of wider machine learning programs. Let us first consider what ML can and cannot do to address unfairness and representation in a general setting. This is important for librarians to know. Librarians offer education in information literacy. Knowledge of the properties of ML will increasingly become a core aspect of this. Then we will look at ML unfairness, representation, and classification, specifically in the case of librarianship. 5.7.1 Fairness, Distributive Justice.
The economic, political, and social frameworks that each society has, its laws, institutions, policies, etc., result in different distributions of benefits and burdens across members of the society. These frameworks are the result of human political processes, and they constantly change both across societies and within societies over time. The structure of these frameworks is important because the distributions of benefits and burdens resulting from them fundamentally affect people's lives. Arguments about which frameworks and/or resulting distributions are morally preferable constitute the topic of distributive justice, Lamont in favor 2017.
ML has little or nothing to add to the vast and supremely important topic, or concern, of being fair, the topic of distributive justice. ML is statistics concerning facts. It does not offer moral guidance. However, ML can itself supply facts that allow decisions to be made. Also, research in ML has also produced some surprising results concerning fairness, e.g., some obvious strategies for being fair can harm the folk they are trying to be fair to. We need some background to introduce ML into a discussion of being fair and unfair. Assume a classification is going to be done into two classes on the basis of a single numerical score, C, for example, Wattenberg, Vegas, and Hart 2022, and Hart, Price, and Schrebro 2016. These classes are used to make a prediction for entities that are being classified, and resulting prediction is either correct or incorrect. An example might be a judgment on whether a person will pay back a mortgage, using creditworthiness as the numerical score. We have information, or data, on the past scores, and we also have information, or data, on whether the borrowers paid their mortgages back. The data may be like this. The intention here is to depict that anyone represented by a red, i.e. with a credit score between 0.4 and 1.5, failed to repay their mortgage, whereas everyone represented with a green, i.e. with a credit score between 2.4 and 3.6, did repay their mortgage. It is easy in a case like this to put in a credit score that classifies or divides the borrowers into defaulters and repayers. Having a credit score of 2 or above will do it. This putting in of a cutoff line, a threshold classifier, is a theory that works perfectly on past data, and we will assume that it holds good with future data going forward. It is a theory that may have been devised by ML, or it may have been produced in many other ways. After all, mortgage companies had similar theories long before the arrival of ML. Problems with the theory start to arise if in the actual data these two regions overlap, say. With the data depicted in Figure 8, there is no way of putting in a classification boundary that does not make some errors. There are two kinds of errors that might be made in respect of repayment: false positives and false negatives. The false positives are where the classification suggests that borrower will repay, but the borrower does not. The false negatives are where the classification suggests that borrower will not repay, but, actually, the borrower does repay. For example, say a boundary was at credit 2.0, as in Figure 8, there is one false positive and one false negative. Of course, in a real case there might be thousands of borrowers and hundreds of false positives and false negatives. No matter where the cutoff line is put, there will be errors of these kinds. It is inevitable with this data. Statistics has techniques for adjusting theories so as to minimize errors. We will not invoke those here. Instead, we will leave this part of the discussion noting that likely there will be false positives and false negatives. Please see Appendix B for further explanation of false positives and false negatives. That there are going to be errors is not a good result. Maybe the composition of the single score could be improved so as to separate the classes. This single number creditworthiness score would typically be an amalgam of many other numbers, i.e. features, for example, salary, number of years of employment, family size, etc., adjusted with weights to reflect their importance. A DL approach would typically add features. Any features not required would just end up with weight 0. This might help. But there will always be other general worries about the training data, whether the sampling properly represents the target population, whether the data on the features and the predictions, the labels, are correct, and so forth. A prudent conclusion might be that there will always be errors. There is another aspect to what we know and what we do not know here. We know only probabilities. We do not know of a particular future borrower whether that individual borrower will repay. We know, for example, of borrowers like that borrower, i.e. ones with the same credit score, that, say, there is a probability of 90% that they will repay. Let us move on from a factual judgment on who is going to repay, to policy. Just as far as the actual lending goes, the mortgage company does not have to act inexorably on the advice or prediction of its repayment theory. It may have other reasons for lending or not lending. For example, it may have only so many funds to disburse and thus be forced into not lending to some clients whom the company knows would be perfectly good repayers or would have a very high probability of repaying. Let us now understand the cutoff in a slightly different way, as a major input to policy regarding future applications, that it is a main factor in separating those suitable for a loan from those not suitable. The boundary of suitability can be adjusted to alter the proportions of false positive suitables or false negative unsuitables. For example, the mortgage company could potentially loan to every applicant, i.e. the cutoff would be at a credit score of 0, then there would be no false negatives, but, presumably, a number of false positives. Or, it could move the cutoff far to the right and have no false positives, but a number of false negatives. The mortgage company has choices. There are going to be errors. But the kinds and numbers of errors can be manipulated. Now let us introduce fairness. Among the features in the single number creditworthiness score there may be values for attributes, for categories, that would merit scrutiny in the context of bias and fairness, for example categories like gender and race. In this area of research, these categories are known as protected or sensitive features or categories. Let us introduce a fictitious sensitive category, shape, which has two values, circle, cross. We can show these on our diagram. Is our theory unfair on shape? What might bias mean in this context? How might we counteract bias? For the moment, let us set aside the question of whether shape, e.g. being a cross, may cause a borrower to be a better or worse repayer. We will come back to that. Here are some suggestions: Hart, Price, and Srebro 2016, Corbett Davies and Goel 2018, Kussner et al. 2018.
Approach 1, unawareness or anti-classification. Ignore the property of shape. The suggestion is that it is unbiased, or not unfair, over shape, inasmuch as it ignores shape. Analogically, in a more realistic setting, the suggestion is that one way to avoid bias over race and gender is not to have, or not use, any data on race and gender. There are two problems with this, though. Shape, or race or gender, may be correlated with other features that have the potential to serve as proxies for the protected attributes. For example, maybe all the crosses live in one zip code, and the circles in another zip code. Then a strategy of ignoring shape, but using zip code, may lead to, or reveal, unfairness on shape even though the algorithm does not directly use data on shape. It is better to have data on shape and to prove that the algorithm produces fair results, using an acceptable definition of fairness and a technique for achieving it. The second problem is that the protected attributes may indeed have a causal relation to the predicted outcome label. It may be that the crosses are better repairs than the circles, so omitting information on this may produce a theory, a cutoff, that is less accurate, leads to more false positives and false negatives. This may seem unlikely or implausible in a mortgage repayment example. But in a medical setting, it is known that there are many differences between the races and genders. Whites, in the U.S., are more prone to certain heart conditions, e.g. atrial fibrillation, than other races, Doolin et al. 2013. Sickle cell anemia is predominantly a disease of those who live in sub-Saharan Africa, and descendants of earlier residents of that region, Rees, Williams, and Gladwin 2010. Women, and not men, have reproductive systems for bearing children. Men, and not women, are exposed to the possibility of prostate cancer. Women live longer than men. It seems that information on race and gender would be useful in medical settings. The systems would need to be fair in their uses of that information, but not using the information at all does not seem to be the right move. Ignoring sensitive attributes can lead to unfairness with those the system is trying to be fair to. Female violent felons have a lower rate of recidivism than do male violent felons. Omitting gender from recidivism calculations may lead to harming women. Approach 2, demographic parity. Separate the data into two sets of data, two graphs, one for circles, the other for crosses. Then, potentially, use a different cutoff for each, ensuring that the same proportion are candidates for loans. So, for example, if there are 1,000 crosses, and the cutoff for crosses leads to 10% of them qualifying for loan, then set the cutoff for circles to ensure that 10% of them qualify, whether there be 100 circles or 10,000 circles. Some defense can be made of this, in certain circumstances. But consider the true negatives, on either graph. It may be that a mortgage company, following the demographic policy, has to lend to borrowers that they know will not repay. At an extreme, say all the crosses repay and none of the circles do, i.e. repayment is causally related to a protected attribute. If 10% of the crosses are offered loans, then the demographic policy requires that 10% of the circles also be offered loans, even though they are not going to repay. This actually does not seem fair to anybody, or to the company. Approach 3, equal opportunity. Again, separate the data into two sets of data into two graphs, one for circles, the other for crosses. And, again, there will be two cutoffs. But this time the cutoffs focus only on those who are judged to be repairs. Then, the cutoffs are set to ensure, insofar as it is possible, that the same proportion of circle repairs and the cross repairs are offered loans. If you are classed as a repair, there is equal opportunity of being offered a loan, whether you are a cross or a circle. Wattenberg, Vegas, and Hart 2022, and Hart, Price, and Srebro 2016, favor this approach. Presumably there is the problem with it of false negatives. Say you are a repaying cross. Some of those are going to be incorrectly classified as non-repairs, i.e. they are false negatives. But once they are, wrongly, classified as a non-repair, they will not have an equal opportunity of anything. They are not going to be offered a loan, and nor do they have a chance of being offered a loan. It may be that equal opportunity is fair for the group but not necessarily fair for every member of the group individually. Approach 4, Counterfactual Fairness, Kussner et al. 2018, suggests the following. Work with individuals only. Then require, and prove, that the probability of getting a loan for any individual, who is actually a cross, is exactly the same as the probability of that same individual getting a loan, had that individual been a circle, i.e. counterfactually being a circle, and similarly in the other direction, from circles to crosses. That is, data on sensitive attributes is obtained and used. But it is used to show that the outcome results would be the same for all individuals even where the values of those sensitive attributes were different. This approach certainly plumbs a central intuition. For example, under it, with race, whether you are black or white does not matter as far as your probability of getting a loan is concerned. While counterfactual fairness is different conceptually to demographic parity, Rosenblatt and Witter have proved that the two lead to equivalent outcomes, Rosenblatt and Witter 2022. Demographic parity is easier to work with.
To sum up, fairness in ML algorithms is an active research area. There are a number of proposals. Most of them have merits and shortcomings. Since there are probabilities involved, with false positives and false negatives, it seems unlikely that any suggestion on fairness in ML can, at one and the same time, be fair to all individuals, to all groups, and to all related parties. Most of the proposals can be proved mathematically to hold, or not hold, of the relevant ML systems. There can be evidence and accountability. Which theory of fairness should be used is not a matter for the ML programmers to decide. It belongs with distributive justice, and it is a decision for the wider constituents. There is a take-home here. If there is a test that has false positives and false negatives, and pretty much all real-world tests do, medical tests, driving license tests, law school admissions tests, etc. And if some, many, or most of the false positives have some other property, say, having the race of green, or being a cross. Or if some, many, or most of the false negatives have some other property besides testing negative, say, having the race of red, or being a circle. None of that, by itself, means that there is any evidence whatsoever of unfairness. Further analysis is needed, further statistics, or further mathematics. Epidemiologists, one group with a knowledge and interest in these methodologies, have tools at their disposal. One is causal diagrams. The use of causal diagrams, with appropriate data, can provide fallible evidence for fairness or unfairness. Causal diagrams are explained and discussed further in Appendix C. 5.7.2 Debiasing representation. Man is to computer programmer as woman is to homemaker. Balak-Bassi et al. 2016, that attention-grabbing question, or phrase, is part of the title of an important paper by Balak-Bassi et al. What they are alluding to is that natural languages have associations in them which reveal assumptions about gender stereotypes. Sometimes these assumptions are innocent, harmless, and possibly even useful, such as the association between being a queen and being female. Often, though, associations between words can be suspect and perhaps even revealing of undesirable underlying biases, such as that between receptionist and female. A problem in the context of ML is that if ML uses natural language as data, and it often does, the resulting ML programs might entrench or even amplify the biases. While this Balak-Bassi paper focuses on gender stereotypes, it also would have application with racial or religious or other stereotypes. See also, Kaliskan, Bryson, and Narayanan 2017. This type of bias is different to the unfairness biases of allocation, for example, as to who gets mortgages and who does not. Rather, this is to do with biases of representation, with natural language processing, NLP, and with removing unwelcome stereotypical associations. Natural languages change, of course, and unwelcome stereotypical associations come and go. How to interact with that in a positive way is a larger question. But reducing bias, or debiasing, text which is used as input data to ML is a distinct possibility. The Bollock-Bossy paper has definite sound proposals on this. It is not being asserted here that text for ML can be purified perfectly. However, the text can be improved, and it should be possible to ensure that ML programs do not amplify existing biases in language. There can be other harms of representation in addition to those strictly in NLP. For example, there can be such harms with the labeling of images, the attachment of metadata to images. In the case of the single-sentence characterization of an image, there might be denying people the opportunity to self-identify, reifying social groups, stereotyping, erasing, and demeaning, and probably further types. Wang et al. 2022. 5.7.3 Panopticon Bias, the Panopticon Gaze. Certainly computers, artificial intelligence, and ML are enabling surveillance as never before. Examples of this are readily available in librarianship. There are recommender systems which can recommend books, articles, music, films, etc. that individual patrons might like. But to do this, the systems have to know what at least some patrons have read or explored in the past. Likely, patrons will have to give up some privacy to get the value-added intermediation of recommender systems. A more extreme example is that facial recognition software could track everything that every patron does in a physical library. This would be completely against the ethos of librarianship. Facial recognition technology certainly raises questions. It is a technology that allows the identification and tracking of individuals. These days it is pretty good in a technical sense, i.e. good at identifying and tracking. But, Nick Thiem asserts,
AI's unique talent for finding patterns has only perpetuated our legal system's history of discrimination. Since people of color are more likely to be stopped by police, more likely to be convicted by juries, and more likely to receive long sentences from human judges, the shared features identified are often race or proxies for race. Here, computational injustice codifies social injustice. Theme 2018.
Joy Buolamwini has written on topics related to this. One of her early papers observes that she, a person of color, was largely invisible to computer systems. Then later she offers the view that computer facial recognition was a technology of discrimination against people of color. Buolamwini 2019, 2016, Race, Technology, and Algorithmic Bias 2019. The American Library Association also have a piece, now mildly dated, American Library Association 2018. We can all agree that recognition and tracking is a creepy technology that seemingly we can do without. Or can we? There are many occasions when there is a need to know a person's identity, i.e. who the person is. In librarianship, there is the need to know who the patron is that is checking out the books. To establish identity, there needs to be some gold standard, some difficult-to-forge validator whose original is on file or permanent record somewhere. Biometrics offers a way in here. It can use images of faces, fingerprints, images of irises, DNA, and similar. Right now, facial images are by far the best combination of ubiquity and convenience. More or less everyone in the U.S. has ID, identification, and that ID is going to be a driving license, a real ID equivalent, a passport, a green card, or similar. All of these carry an image, a photo, identifying the holder of the ID. We can add to this folk who unlock their smartphones using a scan of their face. Facial recognition itself is now so good that it can recognize a person, in person, from a suitable image with 99% or more accuracy. Quite what this 99% figure means is another question. Let me insert an anecdote. In June 2023, the author flew from Dallas to Paris on American Airlines. When boarding, he walked straight onto the aircraft in seconds, being identified by facial recognition. The airline, along with many others, already had a scan of his passport. Now, this facial recognition presumably was being trialed and not mandatory. But, also presumably, objectors would have had to produce their passports, to have printed and produced their boarding passes, and to have spent minutes with these processes. There will be no need to make facial recognition mandatory for these kinds of circumstances. We will all want it, for convenience. We will be falling over ourselves to get it. Hot off the press, The Independent headline July 18, 2023 Eurostar passengers leaving London can skip passport checks with new facial recognition tech. Separately, more than a few sporting venues use facial recognition technology to identify season ticket holders and to admit them without fuss or muss. G2023. The U.S. Immigration and Naturalization Service use facial recognition at airports to identify persons of interest. The author has been through INS at U.S. airports many times. Every time until recently the INS agent took his fingerprints. On coming back from Paris in 2023, this did not happen. The agent told him that it was no longer necessary. Who knows why? INS must have had all the identification they needed. Perhaps from facial recognition? It is hard to see all this being rolled back. Facial recognition has uses which are absolute winners. Of course, tracking people 24 hours a day, 7 days a week is an entirely different matter. There are companies, e.g. IBM, who say they will not sell this technology to the police. Peters 2020. There is an important difference between being recognized through a driving license in a pocket and being identified by facial recognition. Ordinarily, an officer of the law, or similar, would have to ask to see a driving license in a pocket, and the person asked might consent or refuse to reveal it. Then this kind of transaction would not scale, say to 10,000 people in a crowd at a protest. Facial recognition, though, can work with or without assent, and it scales easily to many thousands of faces. 5.7.4 Bias in Librarianship Classification. This topic is included in Chapter 7 Machine Learning Bias and Librarianship. 5.8 Stochastic Psittacosis, Large Language Models and Foundation Models. The three reports or papers on the opportunities and risks of foundation models, Bomasani et al. 2022, Language Models are Few-Shot Learners, Brown et al. 2020, and on the dangers of stochastic parrots. Can language models be too big? Bender et al. 2021 have a wealth of material on potential harms arising from large language models or foundation models. We need to be aware of some of the problems. Large language models are large, no surprises there. Then what they do, essentially, is close tasks. See Section 3.5 for an explanation of closed tasks. This can lead to many other abilities, question answering, chatting, reasoning, etc. Nevertheless, what seems to be happening is probabilistic symbol manipulation on a grand scale. There is no doubt that some of these systems would pass the Turing test, which at one point in time was taken to be an indicator of whether a system had intelligence, API and Dow 2021. Nowadays received opinion is that the Turing test is not demanding enough. There is the open question of whether there is emergence here. One view is that as the closed tests, and the models mastering them, get ever more elaborate, something emerges from the complexity, and perhaps that emergent property is true intelligence or even consciousness or sentience. A contrary view is that we can easily fool ourselves over apparently intelligent behavior. Maybe even 50% of the population would think that the ELIZA chatbot is either a real person or some truly intelligent software. The contrarians would just view the LLMs as being more complex symbol manipulators. This debate matters in the following way. We need to be cautious and skeptical towards what these modern sophisticated models have to say and recommend. We do not really know how they work in detail. Nor do we know, or can explain, the reasoning that produces many of the specific results. They have characteristics of a black box or oracle. Viewing them as stochastic parrots to use, Bender et al. 2021, delightful labeled lessons are awe in what they seem able to do. One potential harm is misuse. GPT-3 can write, say English, as well as a native educated speaker. This opens some unwelcome possibilities.
Any socially harmful activity that relies on generating text could be augmented by powerful language models. Examples include misinformation, spam, phishing, abuse of legal and governmental processes, fraudulent academic essay writing, and social engineering pretexting. Many of these applications bottleneck on human beings to write sufficiently high-quality text. Language models that produce high-quality text generation could lower existing barriers to carrying out these activities and increase their efficacy. Brown et al. 2020.
Basically, there is very little that can be done about this. It may become possible for other AI applications to recognize and maybe filter machine-written text. If the writer application always puts in a watermark, some giveaway combinations or sequences of words, it might be easy to recognize AI-generated text. Using a machine to generate text is not always bad. For example, summaries of text, journal articles, and even entire document collections can be exactly what readers require. Another potential harm is bias. Bias is a huge and complex topic, as we have been seeing. Just briefly here we will use Kate Crawford's distinction between harms of allocation, harms of representation, and harms of classification, Crawford 2017. Harms of allocation, e.g. fairness in the availability of mortgages, should be able to be addressed. Within the bounds of sloth and fallibility, unfairness can be detected and remedied. Harms of representation, e.g. Muslim violence bias, Abid, Frické, and Zoe 2021, are a much harder case. There are hundreds of training data sets of English samples. The ones of these that are large and containing substantial source material from the internet, e.g. from Common Crawl, will have some biased content. Then, if the training data has bias, then so too will GPT-4 and similar large models. To address this, there seem to be two central possibilities: to keep the unacceptable bias out of the training data, or to remove the bias from the model's output. Neither of these is promising. The systems use self-supervision on the training data precisely because it is near impossible to curate and label with the quantity involved. It may be that some software could filter the training data in some way, but that might not be entirely suitable. GPT-4, if it is going to have an all-around knowledge, needs to know about biased content, for example, Holocaust denial. It just needs to know that the biased content is biased and to not write biased content when writing in its own voice. Working on the output probably is not much better. Our experience with filters, e.g. using blacklists, on the internet is not good. Filtering the word breasts, for example, to filter pornography tends also to filter breasts in the context of breast cancer. It may be possible with systems like GPT-4 to instruct the systems themselves to remove biases of representation. For example, to provide examples of, say, anti-Muslim bias and prompt the machine to remove material like this from its reasoning and output. Harms of classification also are tricky and require attention. The actual classification categories used to classify people for some purpose, for example, usually or often depend on historical period, culture, and social factors, Hacking 1999. But training data for a foundation model will usually favor one time, place, and culture. This issue is also seen with medical data. There are many labeled sets of medical data, but many of them would not be good as training data. One reason is classification categories and diagnoses can change through time. Views of homosexuality in the 1950s, for example, are different from those of today. 5.9 Supplement: The Bias of Programmers. 5.9.1 The Biases of Professional Programmers. The possibility of programmer biases being encoded, in some way, in their programming artifacts. Contrary to making an error, which represents a single incident in which one makes an incorrect judgment, a bias is a systematic tendency to commit the same type of error over time or in different situations. Johansson, Peterson, and Johansson 2021. This kind of bias has absolutely nothing to do with bias in the sense of being unfair to anyone over race, gender, social status, economic status, etc. A typical workflow process for a professional programmer at work on an individual program is that there will be a specification that the program must meet. There will be a house style, which is how the programs are to be written, for the employer, or for the open source project, or for the intellectual area in question. When the program is first completed, and continuously thereafter, it will be subjected to quality assurance, including debugging. The program will be shown to meet the specification. The programmer will have learned programming in MIT, Stanford, Princeton, Lomonosov State University in Moscow, or in many other worthy institutions, including polytechnics and community colleges. They may even have learned from online sources, or have been self-taught. They will have learned a style of programming. Not every programmer is different from every other programmer. Definitely there are styles among programmers. These are not biases. All programmers make errors, but they will catch most of these in the debugging, and if they cannot, likely the program will not meet the specification. Most of the types of bugs are known. For example, there is an off-by-one error in a loop. We need not worry about what this is. Even the best programmers can make an off-by-one error, but if a programmer has the systematic tendency to make off-by-one errors, i.e. they are biased over this, basically they need to find a new line of work. Johansson et al. Argue that each program probably encodes the cultural and cognitive biases of their creators, Johansson, Peterson, and Johansson 2021. Emphasis added. And they offer evidence to this end. They even offer evidence of priming, that is, they can prime a programmer to exhibit specific cultural and cognitive biases. Theirs is important work. But let us look at how it proceeds. There is a programming task to write or sketch a program, but they omit any real specification for what the program is supposed to do. In this way, they place the programmer in a condition of uncertainty. Then, their method suggests, the programmers reveal their cultural and cognitive biases in their decisions on what the program is to do, what the specification might be, and this can be primed. While this research is important and addresses a rarely researched area, we find it unconvincing. Your mileage may vary. But our mileage is if there are no specifications, all bets are off. There are starting to be other research papers in this area, and Johansson et al. Provide a valuable guide to these, Johansson, Peterson, and Johansson 2021. 5.9.2 The biases of all of us as programmers. Pretty much all of us are programmers. There are 6.5 billion owners of smartphones in the world, Turner 2018, updated to 2022. That is over 80% of the world's population. Those phones likely have applications, apps, on them, and settings. They are configured. That configuration, in conjunction with the host operating system and infrastructure, amount to a suite of programs, a cluster of software and software infrastructure. The owners of the phones, or their friends, or young relatives, or delegates will establish or program the configurations. There is a lot of programming going on. There will be extensive bias in the sense of systematic mistakes in the programming, and also the phone will enable bias, prejudice, in the sense of bringing to light unfair views or opinions about other human beings. The importance of this is that to a large degree how our own smartphones, and similar, are set up are within our own control. We can reduce bias if we wish to. What we need is information literacy and configuration agents to implement the prescriptions. Chapter 6. Bias in Machine Learning and Librarianship. 6.1 Introduction. Let us start this chapter by revisiting the paper by Sue Lin Blodgett et al. On bias and NLP, Blodgett et al. 2020. The abstract to this, in full, is:
we survey 146 papers analyzing bias in NLP systems, finding that their motivations are often vague, inconsistent, and lacking in normative reasoning, despite the fact that analyzing bias is an inherently normative process. We further find that these papers proposed quantitative techniques for measuring or mitigating bias are poorly matched to their motivations and do not engage with the relevant literature outside of NLP. Based on these findings, we describe the beginnings of a path forward by proposing 3 recommendations that should guide work analyzing bias in NLP systems. These recommendations rest on a greater recognition of the relationships between language and social hierarchies, encouraging researchers and practitioners to articulate their conceptualizations of bias i.e. what kinds of system behaviors are harmful, in what ways, to whom, and why, as well as the normative reasoning underlying these statements, and to center work around the lived experiences of members of communities affected by NLP systems, while interrogating and reimagining the power relations between technologists and such communities. Blodgett et al. 2020.
This paper is very thorough in its reasoning, evidence, and citations. Please read it. We will take from it its 3 recommendations, applying them to librarianship. 1. Recognize the relationships between language and social hierarchies. 2. Encourage researchers and practitioners to articulate their conceptualizations of bias i.e. what kinds of system behaviors are harmful, in what ways, to whom, and why, as well as the normative reasoning underlying these statements. 3. Center work around the lived experiences of members of communities affected by the systems. Some material for the first recommendation is in Blodgett et al. 2020 itself. The third recommendation requires extensive outside empirical research which we are not equipped for. That leaves as our focus:
what kinds of system behaviors are harmful, in what ways, to whom, and why, as well as the normative reasoning underlying these statements.
There is a vast literature on bias in information provision, and, of course, information provision includes librarianship. But much of this literature has a wider ambit than librarianship. It wants, for example, to interrogate internet companies and power structures of one kind or another in society as a whole. No comment is passed on that here. We need focus on ML. There is an intersection of ML, bias, and librarianship, which we will explore shortly. But, as a summary of what is to come, there is a problem with data. ML needs data to learn from. But at least some potential data from traditional librarianship might have unwelcome aspects to it. For example, an ML program could easily learn the cataloging task of applying Library of Congress subject headings, LCSH, to new books and resources. But some fear that the LCSH labels themselves are suspect. So, according to some, bringing ML into it would just be to reify white supremacy. Cordell 2020. 6.2 Harms of Omission. In Christianity, no doubt among other places, there is the distinction between sins of commission and sins of omission. The first is doing something that should not be done, the second is failing to do something that should be done. Similarly with harms associated with ML, some are harms of commission, others harms of omission. When Crawford et al. Discuss bias in terms of harms of allocation, harms of representation, and harms of classification, surveillance, and Suresh and Guttag extend this out to 7 harms. These are all harms of commission. Crawford 2017. Suresh and Guttag 2021. But information providers, including librarians, also have an interest in something different. Provision is an aim, or to use a word with a wider span, service. Failure to provide service can be a harm. It would be a harm of omission. Harms of omission are a little harder to deal with at a methodological level than harms of commission. With a harm of commission, what or who did it, the causal agent, is available. Whereas with omission, what or who did not do it, the absent causal agent, often needs to be identified and may not be identifiable. 6.3 What to digitize. As mentioned in Section 1.2, ML algorithms need input data in the form of computer digital text, i.e., as structured sets of zeros and ones. For text sources, or text corpuses, that are not born digital, this raises the question of what to digitize. In some areas, the practice certainly has been to digitize primarily what might be characterized as being white, colonial resources, white libraries, newspaper collections of white newspapers, and so forth. This is a tricky area. We know from the fate of the Google Book Project that many do not want their resources digitized, or even the resources of others, see Chapter 1.2. Also, we know that many peoples, tribes, or indigenous peoples do not want some of their cultural artifacts recorded at all, let alone digitized. Perhaps the ML research and practical initiatives can stay on the sidelines in this debate. As Elizabeth Loring et.al. write, concerning the Library of Congress's role.
The technology itself will not be the hardest part of this work. The hardest part will be the myriad challenges to undertaking this work in ways that are socially and culturally responsible, while also upholding responsibility to make the Library of Congress's materials available in timely and accessible ways. Loring et al. 2020.
6.4 Search, primarily using search engines. Search is a filter. The searcher is initially faced with some pages, a site, a collection of sites, or the entire internet, then search reduces the rich vista to something suitable for the occasion. The vista is filtered. There are different possibilities here, and different possibilities for distortion or bias. If the search algorithm uses keywords, spelling correction, semantic correction, stemming, etc., various mistakes or manipulations can occur. Louis Rosenfeld et.al. report that an early instantiation of a search engine on Amazon responded to searches for the subject abortion with the question, "Do you mean adoption?" Rosenfeld, Morville, and Durango 2015. This suggestion is rather more than spelling correction. It is also regularly reported that various configurations of search engines misdirect searchers for abortion providers to adoption agencies. Search sometimes works via recommender techniques, comparing the searcher and the searcher's task to similar searches by other patrons. What happens here depends on which groups the search is compared with, and this can be, in some sense, fair or biased. Usually, a search returns a list of links in order of relevance. Now, relevance is topic, person, and occasion dependent, Frick 2012. It depends on the keywords, the person searching. Different people may get different results from the same keywords, and the occasion, the same person may get different results from the same keywords on different occasions. The latter two features or aspects depend on the degree to which the engine is tracking the user, and the engine does need to be aware of previous searches in order to disambiguate, narrow, and help the user. There is also manipulation of various kinds. For example, there is search engine optimization, SEO, which is tricking the engine algorithms to place some URLs or links higher than they otherwise would be. It is known that most users will not look beyond the first few links that are returned from a search. This might not matter for the supply of pure information. But, for example, if you were a commercial entity, you would prefer to have the links to your products within those first few. The provider of the links prefers this, not necessarily the user. There are companies that provide those services. The returns may thus be affected by paid interests, such as advertisers, retailers, or political groups, although most engines will identify paid links. The search engine companies try to identify the techniques of SEO and to immunize or neutralize them. It is a continuing battle. But even among algorithms that rank by genuine merit, there can be different, and sometimes equally acceptable but orthogonal, views of merit. Orthogonality here means this. Consider the example of sports cars. Is the one that goes faster better than the one whose looks are more head-turning? Or vice versa? It is hard to know. The two properties are orthogonal, they are independent one with the other. Search is a filter infused with judgments and values, and orthogonality. Some areas of the internet are cesspits. That is one side effect of ease of content creation and freedom of speech. Safiya Noble, in her book Algorithms of Oppression, How Search Engines Reinforce Racism, reports that her 2009 search engine query for black girls returned the porn site hotblackpussy.com as its first hit. Later studies 2011 onward produced similar results for the search black girls, and also for searches for Asian girls, Asian Indian girls, Latina girls, white girls. One conclusion that Noble draws is,
girls' identities are commercialized, sexualized, or made curiosities within the gaze of the search engine. Women and girls do not fare well in Google search. That is evident. Noble 2018.
These specific results have changed out of all recognition now, 2023, possibly in part as a result of Noble's research. What a search engine returns for a query does not depend solely on the query. It depends also on who is asking the query. That is what personalization does, and the occasion and history of the question being asked. Having the query black girls, and similar, answered with links including porn sites certainly gets our attention. But what specifically is the harm here, and who is being harmed? Some of the folks asking this kind of search question might be offended by this kind of answer, and some might not be, and some may even be pleased by it. Working to correct offense is tricky, which is not to say that it is not worth doing. The harm seems to be elsewhere, with girls, in general, and of having their identities commercialized, sexualized, or made curiosities. It is a harm of representation. Search engines have made adjustments in this area. Some years ago, when the World Wide Web was just starting, there were curated pages of links on topics. These pages were authored by humans. For example, Lycos and Yahoo did this. These curated pages are like bibliographies, even annotated bibliographies, that a librarian might produce. They did not have or use keywords as lead-ins. Had there been a curated page on black girls, it may well have been neutral as to range of topics, and so far as that is possible. Nowadays, there are just too many pages and too many links to make this practical. Certainly, there are pillar pages, or topic clusters. See, for example, Clarion Creative Agency 2022. These are somewhat similar to the old, curated pages, but likely they will have been generated by computer program, possibly a ML program. If, in a reference interview, a reference librarian was given the keyword string black girls, they almost certainly would think that it is underspecified. A librarian would ask for clarification and disambiguation. Search engines sometimes do that, with overly long keyword strings, but generally they are in the realm of guesswork. Once a search engine has an initial return click among first list of links, it can usually improve the suggestions. So, usually searching is a process, not a one-shot question and answer. Also worthy of mention are autocomplete, autosuggestion, and trends. Google, to take an example, will autocomplete a partial search string on the Google Chrome browser. Here's what it did for the author on October 27, 2022 for black girls. We do not see anything untoward in that list. Google explains how autocomplete and trends work on the page. https://support.google.com/websearch/answers/7368877 zippy equals %2 where autocomplete predictions come from. In part, this reads:
Autocomplete is a feature within Google Search that makes it faster to complete searches that you start to type. Our automated systems generate predictions that help people save time by allowing them to quickly complete the search they already intended to do. Where autocomplete predictions come from. Autocomplete predictions reflect real searches that have been done on Google. To determine what predictions to show, our systems look for common queries that match what someone starts to enter into the search box, but also consider the language of the query, the location a query is coming from, trending interest in a query, your past searches. These factors allow autocomplete to show the most helpful predictions that are unique to a particular location or time, such as for breaking news events. In addition to full search predictions, autocomplete may also predict individual words and phrases that are based on both real searches as well as word patterns found across the web. Difference between autocomplete and Google Trends. Autocomplete is a time-saving but complex feature. It doesn't simply display the most common queries on a given topic. That's why it differs from and shouldn't be compared against Google Trends. Google Trends is a tool for journalists and anyone else who wants to research the popularity of searches and search topics over time.
Notice here that autocomplete adapts to the user. One general point to be made in all this is that the search engines are in competition one with another. They have incentives. In broad sweep terms, they need to be providing what the users want or need, or what is useful or valuable to them. Nowadays, Google has dominance with search engines. But that was not always so, and it does not have to be so going forward. There are various kinds of anonymous, non-tracking engines, and also straight-out competitors. In the absence of diktat, the users will choose. 6.5 Social media, disinformation, misinformation, and false information. It is a jungle out there, and some ML programs have the potential to make the situation worse. ChatGPT can write English better than most English native speakers and writers. Essentially, readers would have difficulties in judging that ChatGPT English output had been written by a machine. ChatGPT could write disinformation tirelessly 24 hours a day, 7 days a week. There is not much that librarians can do about this, apart from providing good education on information literacy. It may be that other ML programs, or even ChatGPT itself, could detect that samples of written English had been written by a machine. This might be somewhat similar to plagiarism detection software. But being written by a machine does not of itself have to be bad. ChatGPT can abstract or summarize text. Summarizing today's newspapers or this month's research journals might be welcome and valuable. 6.6 Bias in the organization of information. 6.6.1 Introduction. Traditional librarianship has devised such techniques as the organization of information, content and container classification, abstracting, indexing, the use of surrogates, controlled vocabularies, thesauri, and the like. Chan 2007, Rowley 2000, A.G. Taylor 2004. There are questions of bias associated with these processes. To mention some. Access to information, for individuals or groups, can be encouraged or discouraged. Straight-out knowledge, or viewpoints, or theories, or beliefs or nexus of values can be conveyed or imparted. Attitudes towards the information resources themselves, including cognitive attitudes in the sense of social epistemology, Fawless 2006, can be manipulated. Mill's diversity of views, Mill 1869, can be promoted or obstructed. Aristotle's diversity in the components of a good life, Wilburn 1999, can be promoted or obstructed. Potentially, there are many topics that could be discussed here. We will restrict ourselves to a few. 6.6.2 Be careful and sparing with emotive content. The use of emotive content is valuable in advertising. It can help to sell things. It is also valuable in literature itself. It can manipulate our attitudes in liking or disliking characters and into becoming engaged with the story. Librarians need to be careful with this, though. Any keywords, tags, subject labels, index terms, and so forth need to be low on emotive content. They need to be neutral. The reasons are, emotive content can produce harms of representation, and the use of emotive terms in indexes, say, or other stepping stones to content, will distort access. ML systems should have little or no problem with avoiding emotive content. Large language models can just be prompted not to use emotive content. Some of the modern systems may be able to be given one example, one shot, and then they will minimize emotive content. 6.6.3 Warrant and controlled vocabularies. A question is, where do the terms in a controlled vocabulary, CV, come from, and what is the evidence or justification for introducing and using the particular terms that are used in a specific CV? There is a word or concept for this consideration. It is warrant, Barite 2018. Warrant is important to us. It is one point where bias might arise. There are different theories of warrant. We will briefly mention three: literary warrant, user warrant, and cultural warrant. Before explaining those, let us introduce a sample potential term for inclusion in a CV or some CVs: gypsy moth. This is an example of a term that might have bias. Sabrina Imbler tells us in a 2021 article entitled "This Moth's Name is a Slur." Scientists won't use it anymore that.
The Entomological Society of America will no longer refer to common species of insects as gypsy moths and gypsy ants, because their names are derogatory to the Romani people, Imbler 2021.
The article continues in part.
For Ethel Brooks, a Romani scholar, the move is long overdue. As a child in New Hampshire, Dr. Brooks loved watching worms and caterpillars crawl across her hand. But one particular caterpillar, the hairy larvae of the species Lymantria dispar, terrified her. The larvae would swarm and strip the leaves from a tree, leaving behind so much destruction that people sometimes called them a plague. But no one blamed L. dispar. Instead, they blamed gypsy moth caterpillars, the species' common name. That's how they see us, Dr. Brooks remembered thinking as a child. We eat things and destroy things around us. Dr. Brooks, now chair of the Department of Women's, Gender and Sexuality Studies at Rutgers University in New Jersey, has spoken out against the use of the pejorative in fashion and college parades, she said. But Dr. Brooks never imagined the pejorative could be stricken from its use in the more staid realm of science. It's hideous and super racist and it's hurtful, she said. But what can you do about it? Imbler 2021. To put some editorial interpretation here, Dr. Brooks is probably talking of the word gypsy as being super racist, not the phrase gypsy moth.
The name gypsy moth, or gypsy moth, its British spelling, has not just been used for insects. Around 1930, the de Havilland Aircraft Company produced the moth series of aircraft, which included the gypsy moth, and the related tiger moth, puss moth, hawk moth, swallow moth, hornet moth, etc. When the supply of war surplus 8-cylinder engines ran out, Geoffrey de Havilland designed the powerful and reliable 4-cylinder gypsy engine, which was then used in the gypsy moth. The Prince of Wales owned a gypsy moth. You can see him portrayed flying it on the television series The Crown. Amy Johnson flew a gypsy moth single-handed from Britain to Australia, roughly 11,000 miles, at a flying speed of 100 miles per hour.
No other planes in their time and place so thoroughly served the advance of aviation and civilization in so many diverse ways as the de Havilland moths, Harris 2002.
Separately, Gypsy Moth 4 is the ketch that Sir Francis Chichester sailed single-handedly around the world in 1967. Chichester had worked earlier on the Gypsy Moth aircraft. It is reasonable to assume that Jeff de Havilland and Francis Chichester were not intending to demean their creations in any way by their choices of words gypsy or gypsy moth. Quite the opposite, the names were intended to be positive descriptors. After all, de Havilland was selling mass-produced airplanes. Then the items described, the engine, and the aircraft, turned out to be superlative. Additionally, Amy Johnson, the aviatrix, was one of the most influential and inspirational women of the 20th century, Gillies 2020. All was good for Gypsy Moth in these domains, these periods, and these cultures. It is hard to imagine that any Romani were offended by Gypsy Moth in the 1930s. The idea of literary warrant comes from E. Wyndham Hume at the beginning of the 20th century. Lois Mychon et.al. Summarize it.
The basis for classification is to be found in the actual published literature. Barite 2018, Chon, Richmond, and Svenonius 1985.
There is a slight difficulty or ambiguity here. What is actual published literature? In 1911, that would have been published physical books that could be placed on shelves in libraries. But nowadays we have digital publication, e-books, web pages, the internet, and so forth. We need to take a wider view. Nevertheless, literary warrant would provide a motivation to using Gypsy Moth in the 1930s, in the 2020s, and in the 2020s about historical 1930s literature, both in the sense of identifying an insect and identifying a training aircraft. Computers would be a great help here. The software does not necessarily have to be ML software. The processing has to look through the actual published literature, which it will be able to do really well for all literature available in digital form. Notice here that with literary warrant there is one CV for all, whatever the area of focus is for that CV. The actual published literature is the same for everybody. It is not one thing for one group of users or culture and another for a different group of users or culture. User warrant focuses on the user. It is the user or the patron, or, God forbid, the customer, that is trying to find the resources. Identifying the users is not the easiest, nor is identifying how they do their searches. In the case of a public library, using say Dewey Decimal Classification, one might take the view that the users are the public. But it is also possible to be more granular than this. Patrons looking for materials on insects likely will be a different group to those looking for resources on historical aircraft. If the CV is for a smaller and more limited collection, e.g. for the index for a catalog for an aircraft museum, the tasks may be easier. Once again, computers are a great help. If patrons type into some kind of search box or online public access catalog or discovery system, it will be easy to know what searches are being carried out. Nowadays most searches will be free text searches. The patrons can type in whatever they like and the software will learn what they do like. This time there can be several different CVs for the same collection of literature, one for one group of users of that literature and another for a different group of users of the same literature. Search software can personalize searches, as it would do for a private computer at home as opposed to in a public library. Cultural warrant focuses on the cultures of groups of potential users of the resources. It is similar to user warrant in that there can be several different CVs for the same collection of literature, one for one culture of users of that literature and another for a different culture of users of the same literature. There can be obvious benefit in localizing some CVs to place, time, beliefs, lifestyle, etc., i.e. to culture, no matter what literary warrant or user warrant might suggest in these cases. For example, legal systems can vary from state to state and country to country. What are library practices here, and how can ML help or hinder? Typically, librarians will use universal systems such as LCC, LCSH, DDC, to catalog or provide metadata for their resources. These CVs depend largely on literary warrant, sometimes with cultural adjustment. There is widespread dissatisfaction with these CVs, particularly with cultural aspects. For example, Elizabeth Lorang et. al. Wright.
Previous and ongoing collecting and description practices. We're in our colonialist, racist, hetero and gender normative, and supremacist in other structural and systemic ways. Lorang et al. 2020.
Assume so. Were ML to use these practices going forward, presumably it would just entrench them. Mind you, if existing cataloging practices continue as is, without ML, there also presumably would be entrenchment. ML does have the capabilities of correcting whatever shortcomings a CV might have. It certainly can reduce emotive content and provide cultural adjustment where required. Really, some guidance is needed from librarians. For cataloging, librarians need to work themselves towards unbiased universal CVs, and so far as that is possible, ML can help with this, and also with the automation of insertion of values into the metadata fields of the resources. What about Gypsy and Gypsy Moth? LCSH has this. Gypsy. Use subject headings beginning with or qualified by the word Romani for topics related to the Romani people, e.g. art, Romani, Romani poetry. Gypsy Moth, the insect, uses is. Gypsy Moth, training plane. Use moth, training plane. G.PDF 2022. This basically is literary warrant with some cultural correction. Notice, though, that using moth for Gypsy Moth is asking for trouble with the precision of searches, because there are many other kinds of moth training planes, e.g. tiger moth, etc. Let us spell this out. You are interested in books on Gypsy Moth, training plane, so you look up that subject in LCSH and learn that the catalogers have used moth, training plane, for this topic, so you now search for moth, training plane, and your search returns books on tiger moth, puss moth, hawk moth, swallow moth, hornet moth, gypsy moth, etc., most of which you do not wish to have. So, trying to be culturally sensitive, which we all want to be, has come, in this case, at the cost of ruining a search, and providing good searches is one thing librarians aspire to. 6.6.4 The act of classification has consequences. Obviously, in a court of law, classifying the accused as guilty is rather different to classifying him as not guilty, in terms of what the future might hold for him. So too for poisons, grades of scholarship applicants, and most everything else in daily life. And, indeed, so too for being classified black in, now fortunately historical, apartheid South Africa. Whole books have been written largely on this, cf. Boker and Starr 2000. Independently of the particular classification of items, we have noted how the accidental or intentional manipulation of the emotive content of equivalent concepts can affect attitudes to those things named. Here are some of Sanford Behrman's examples from the 1970s and earlier Library of Congress subject headings, S. Berman 1971. Yellow peril, Negroes, etc., mammies, idiocy, idiot asylums, lunacy, Indians of North American, civilization of, slaughtering and slaughterhouses Jews, barbarian invasions of Rome, delinquent women. Classification is also fallible, in common with all human cognitive endeavors. We know this directly from our everyday knowledge that anyone can make a mistake. We know it also from the test-retest unreliability of professional classifiers, catalogers, using precision and highly designed classification schemes, Snow 2017. If a classifier can classify the same item twice in two different mutually incompatible ways, classification is fallible. The act of classification is also subject to bad faith or rogue cataloging. Everyone does this, all the time, pretty well every day. Faculty do it when they call a less than stellar student paper in a. And some professionals do it too, fortunately not so often, perhaps when they have a private attitude or strong feelings, which misdirect their work, and which, for example, might lead them to classify an information resource on abortion in such a way that the resource is difficult to find. Classification is also subject to cultural factors. For example, different cultural groups have different attitudes to suicide, and thus different propensities to classify deaths as suicides, and this means that classification will not be isomorphic across cultures, independently of fallibility and rogue behavior. In sum, the act of classification has consequences, can be used to produce attitude manipulation, is fallible, can be malfeasant, and has a dependency on culture. Some of the harms here are harms of representation, some are of allocation. Allocation can be seen as a harm of commission, doing allocation but not doing it fairly, or a harm of omission, failing to do allocation for certain groups or cultures. 6.6.5 Taxonomies have consequences. Taxonomies that have subclasses, i.e. most of them, make true or false assertions which are claims to knowledge. Asserting that one class is a subclass of another is a factual or conceptual piece of knowledge. For example, if a biological taxonomic scheme has whales as being a subclass of mammals, then it is offering the assertion that whales are mammals. Some of these schemes are intended to be objective, i.e. they represent scientific or mathematical knowledge. Others are intersubjective, for example, the nurse intervention classification mentioned earlier, and those represent decisions or conventions. Some schemes can be problematic. Consider subjects, or topics, like creationism and evolution, which we might be wanting to put into a hierarchical scheme of topics which allows them to inherit from some of scientific theory, false scientific theory, pseudoscientific theory, religious view, and blasphemy. What are we to put where? Well, who knows? Certainly, different groups of people would choose differently, and different groups of people would disagree over which is a right or acceptable or appropriate classification. So, now any classification scheme does not so much contain knowledge, or, at least, uncontroversial knowledge. It does, however, contain or assert a point of view. For example, one scheme might assert that creationism is a false scientific theory. There is a difference here between objective schemes and intersubjective schemes. A mathematical classification that places the integers as a subclass of the reals is objectively right or wrong about that, and mathematicians can provide insight as to which that is. Similar considerations apply to the elements in chemistry or species in biology. Sanford Berman enlightens us that the 1970 Library of Congress subject headings are biased, and he means by this largely that they have unwelcome emotive content. S. Berman, 1971. Berman also locates the bias. It lies with the classification schemes which are
parochial, jingoistic Europeans and North Americans, white-hued. Christian. Heavily imbued with the transcendent, incomparable glory of Western civilization. S. Berman, 1971.
Hope Olson echoes Berman, telling us that the headings reflect
the exclusionary cultural supremacy of the mainstream patriarchal, Eurosettler culture. Olson, 2000.
And Boker and Starr wax long about generalizations of this, that the powerful subjugate the weak by imposing their will through classification. Boker and Starr, 2000. See also, S. Berman, 2000, Knowlton, 2005, Olson, 2002. All right, but all schemes are biased in that they reflect a point of view, or knowledge, or beliefs, or opinions. We have to work with this. It is not an insurmountable problem. As Poincaré once remarked about the indispensability of a point of view when observing,
he is no longer a slave who can choose his master. Poincaré, 1905.
Then there are the conjectured conspiracies, surface or hidden, whereby the strong use classification to batter and imperialize the state of nature blissful. No comment on that here. ML did not cause the problems in older library taxonomies, since they predate ML. However, care is needed to ensure that it does not prolong the issues. It may be used to counteract them. 6.6.6 The current state of libraries and their organizational systems. Melissa Adler writes,
libraries are complicit in privileging and circulating ignorance, inhibiting rather than opening up bodies of literature as sources of various knowledges. Adler, 2017, 2. Editorial note: knowledges, plural, is an unusual form which perhaps has some currency in the sociology, or cultural aspects, of knowledge.
Elizabeth Loring E.T. Al Wright.
Previous and ongoing collecting and description practices, for example, were in our colonialist, racist, hetero and gender normative, and supremacist in other structural and systemic ways. These understandings are the foundation on which training and validation data will be created and assembled. They will become reinscribed as statements of truth, even as we elsewhere champion the potential of computational approaches to uncover hidden histories, identities, and perspectives in collections. To engage machine learning in cultural heritage must mean confronting these histories, committing to the hard work of acknowledgement and rectification, and not simply reproducing them and giving them a whole new scale of power. There should not be a future for machine learning in digital libraries that is not first and foremost committed to, in the words of Thomas Padilla, responsible operations, and to all of the ongoing, cross-cutting work that responsible operations entail. Loring et al. 2020.
The Thomas Padilla work alluded to is Padilla 2019, Responsible Operations, Data Science, Machine Learning, and AI in Libraries, and in turn this cites influence from Rumman Chowdhury, Chowdhury 2023. Padilla writes,
Chowdhury defines responsible operations as collective investments in processes to combat algorithmic bias. Padilla 2019 Note 6, seemingly, the original sources no longer exist.
Padilla's report is a research position paper for OCLC. It is substantial. We will just briefly mention the section on managing bias. Padilla writes,
bias management activities have precedent and are manifest in collection development, collection description, instruction, research support, and more. Of course, this is not an ahistorical frame of thinking. After all, many areas of library practice find themselves working to address harms their practices have posed, and continue to pose, for marginalized communities. As libraries seek to improve bias management activities, progress will be continually limited by lack of diversity in staffing. Monoculture cannot effectively manage bias. Diversity is not an option, it is an imperative. Padilla 2019, 9.
Then he suggests the holding of meetings, holding symposia, convening working groups, etc. 6.6.7 Designing Information Taxonomies for Librarianship. P. Classification and classification schemes are important in helping users meet resources. Professional librarians, and similar, are users of classification, not designers of classification. Almost no librarians produce classification schemes, and, with the advent of copy cataloging, truly few librarians classify resources. Here are some of the balls to be juggled. Classification is the most effective if it is in terms of the concepts, worldview, and values of the users, user warrant as opposed to author warrant. But rarely are the users a homogeneous group. We all of us are simultaneously members of many different groups, male/female, old/young, Republican/Democrat, filmgoers, those interested in sports, gay/straight, etc. And many of these groups truly define a culture. We are all simultaneously members of many different cultures. Which culture, or cultures, is the classification designer aiming at? Presumably, something in the middle. A starting point is for the designer to wind down any emotive content in the scheme and wind up the correct cognitive content. A quiet tone, neutral, always fallible, cultural absolutism would be the starting point. Less emotion and more knowledge generally facilitates access. But designing is not so easy. Let us talk websites for a moment. Consider trying to design a website for the Flat Earth Society. Now, the classification, in terms of that culture, would reflect a point of view, indeed a somewhat extreme and false point of view, not knowledge. So, there is a switch here to cultural relativism. Folk not part of that culture, normal folk, might struggle with using the resulting website. But the site might not have been designed for them, and perhaps this does not matter. Normally, the duties of stewardship require that the information professional get the data right, for example, with credit card bureaus. But a classification designer might have the need to get the data as the users believe it to be, not as it is. The designer might also be asked to increase emotion or manipulate attitude, and not to be neutral. What would be wrong with the luxury jeweler's website classifying some of their diamond rings as truly gorgeous, Prince Charming's choice, sugar daddy's specials, etc.? But then there are cases like a white supremacist's website. Here, let us guess, what the users want is something expressing false views in an extreme fashion, possibly even hate speech. The absolute limits seem to be freedom of speech. If what is envisaged is protected speech, ethically or legally protected speech, then the designer can instantiate it. He or she may have personal misgivings, in which case they should just not undertake a task of the kind that gives rise to worry. There can also be professional and societal misgivings that add caution to freedom of speech, as we will see. Of course, there are many ways computers and websites can change attitudes. For example, there is Captology, the persuasive use of computers, Fogg 2003. 6.7 Navigation, metadata supported and otherwise. Conceptually, metadata for an individual information resource seems to be just a table of field value pairs, where semantically the field value pairs cover container metadata, such as print date, physical location, if these apply, content metadata, such as subject matter, and mixed container content metadata, such as author, title. All this seems to be entirely independent of navigation by a user from information resource to information resource, if such an operation is appropriate. However, this is not quite right. Quite a lot turns on the nature of the values used in the field value pairs. Obviously, one resource may have the same author as another resource, and a patron may want to navigate to other books by the same author. Then dates, as values, have obvious relations to each other, e.g. earlier date, later date, same date. A similar point is true of locations. Then for metadata values for fields like subject matter, the values would likely come from a controlled vocabulary, possibly a thesaurus. Typical thesauri will support generic, instance, and partitive relations. In turn, these support navigation following these relations. For example, a book might have a metadata subject field value of Rapalosera, and a patron might want to navigate to another book, or books, on a similar but more general topic of course. The topic is Lepidoptera, and that topic will be a metadata field value on other books. The metadata is here supporting navigation, but it is doing so in conjunction with a thesaurus or classification scheme. If that classification scheme is biased, the actual navigation might be distorted. In the traditional case, using information resources which were paper pages, structured and co-located into books, placed on shelves, placed in libraries, placed in buildings, the mere physicality of the information resources enhanced certain styles of information resource to information resource navigation. For example, the patron browsed along a shelf from one structured information resource to the next. The use of surrogates, such as cards and card catalogs, liberated this to a degree. You could have several cards for each book, and thus, using the indirection of the surrogate, you could make a book have as many near neighbors as you wished. When computers are used as a tool in classification and navigation, generalization is complete. A computer can easily transform views and presentations, and it can easily provide different views of the same computer information resource locations. Computers also can and will make free and extensive use of surrogates. For example, web links or hyperlinks are surrogates, and there can be thousands of links to the same one web page, and, in turn, those links can be organized and displayed in various ways. The designer can make it easy or difficult to navigate from information resource or collection of information resources to another information resource or another collection of information resources. Navigation, browsing and reading navigation, is a filter. Navigation and search pose similar problems. They can be used to manipulate access. The designer needs to be competent enough to know what might happen. Generally, from diversity considerations, one wants to widen access. But there are many problematic cases discussed in librarian literature: access to dangerous true material, dangerous to the user, e.g. how to commit suicide, dangerous to employer, e.g. how to hack a website and steal credit card numbers from it, dangerous to society, e.g. reservoirs near you and how to poison millions of people using them, access to inflammatory false material, e.g. Holocaust denial literature, and many other cases besides. Froelich 2004. Hauptmann 1988, 2002, M.M. Smith 1997, Wolkoff 1996. Traditionally, librarians have been fairly hands-off. They argued that they have no assured knowledge as to the uses that an information resource will be put to, therefore, as policy, they can just supply information resources and not worry further. Nowadays, they are more cautious. ML should be able to help, no matter what the policy is. 6.8 The need to understand ML bias. Not every librarian needs to be an expert in ML bias, or even to have a good acquaintance with ML bias. Information literacy is a basic part of librarianship. Nowadays that does involve ML literacy. That would be a baseline. Going further, while desirable to those interested, gets you involved in a changeable feast. You won't even be able to survey what is on the tablecloth before the comestibles come and go, transmute, and diversify. 6.9 Ethical arguments to underpin assertions of harms of bias. There are ethical concerns that are the province of all informational professionals, such as freedom of speech, freedom of access, privacy, intellectual property, stewardship, and the like. There are codes of ethics for various professional bodies associated with librarianship. Such codes usually build off distinctions between personal and professional ethics, duties to an employer, to the profession, and to society as a whole. American Library Association 2021. American Association of Law Libraries 2019, Society of American Archivists 2020, IFLA 2012. These can be a great help. More fundamental than any code would be the principles of non-maleficence, do no harm, autonomy, let people choose for themselves, informed consent, give people the requisite information for choice, and perhaps even the golden rule, treat others as you would like them to treat you. And more fundamental still would be rights, duties, and ethical consequences. Chapter 7.
What might natural language processing, NLP, bring to librarianship?
7.1 Introduction. Natural language processing, NLP, is a subfield of computer science and artificial intelligence. It is concerned with enabling computers to interact with natural languages such as English, French, or Chinese. It involves the use of algorithms and computational models to analyze and derive and produce meaning from human language in both written and spoken forms. NLP made a huge step forward with the advent of large language models, LLMs, such as 1. Google's PaLM 2 2023 Pathways Language Model 540 billion parameters, Narang and Chowdhury 2022. There is now AudioPyLM, which is a large language model that can speak and listen, Rubenstein et al. 2023. There is PyLME for robots, Dryas 2023. 2. Databricks' DALL-E 2.0, 2023. 3. Meta's Llama Family, Large Language Model Meta AI, 2023. 4. Microsoft's XLNet Family, Generalized Autoregressive Pre-training for Natural Language Understanding, 2019. 5. OpenAI's GPT-X Family, Generative Pre-trained Transformer 3, 3.5, 4, 2020, 2023. Not all NLP relies on machine learning, or, indeed, on LLMs, but a good proportion does so. While natural language processing primarily addresses natural languages, quite often the resulting software can be applied to images, videos, or sounds. Such software is multimodal. This comes about because the underlying substrate is just numbers. Text is reduced to numbers, and so can images, for example. Then some of the algorithms are equally at ease with numbers sourced from text, numbers sourced from images, numbers sourced from sound recordings, numbers sourced from video, and so on. 7.2 The preprocessing pipeline. An NLP program typically will some preprocessing of the text prior to doing its actual task. Here are some of the steps that might be carried out. Format normalization. This is the conversion of the text to a desired standard format, e.g., by making it all lowercase and removing redundant spaces or special characters. 1. Word tokenization. This will split the string or stream of characters into words or tokens. Usually this would involve looking for spaces, or periods, or separators between groups of characters. 2. Base form normalization. Linguists often view words as consisting of a base form, a morpheme, plus, possibly, a prefix and/or a suffix. For example, the word transportation consists of trans plus port plus ation. There are techniques to get the base form. A. Stemming. This means reduced to their root form. So, for example, consult, consults, consulting would all be stemmed to the root form of consult. The result of stemming does not always have to be a well-formed word. For example, change and changing would be stemmed to chang. B. Lemmatization. There is a similar technique to stemming lemmatization which does reduce tokens to a root word. Change and changing would be lemmatized to change. 3. Parts of speech, POS, tagging. This identifies whether the individual tokens are nouns, or verbs, or adjectives, etc. 4. There also can be the dropping or omitting of stop words. Words like a, and, the, etc. do not carry much information and so usually can be omitted. 5. Dimension reduction. More than a few times there are many more words or tokens in the source than are needed for the processing. For example, a novel might have more than 100,000 words in it, but an algorithm might need only 100 words, the right 100 words, to determine its genre. There are techniques for reducing the amount of input, and thus reducing the amount of time and the cost of the processing. 6. In the case of LLMs, the tokens, the processing units that they work with, would often be larger than single characters but smaller than entire words. These pre-processing techniques are also used occasionally within current librarianship. For example, in classical information retrieval, one approach is to try to match a vector of a query to vectors of documents. With this, tokenization, stemming, dropping stop words, and, possibly, a TF-IDF calculation will have been done on the text of the documents to produce the vectors. To explain the TF-IDF calculation, a simple way of identifying which document, among many documents in a corpus, is relevant to a search is to consider how often a term appears. So, for example, a search for information about Toyota cars might look for how often the word Toyota appears in the different documents. What is desirable is that Toyota appears frequently in the document to be returned, but not frequently, relatively speaking, in the other documents in the corpus. The calculation term frequency inverse document frequency, TF-IDF, determines this. Going forward from the preprocessing, some of the later techniques will use a bag of words approach. With this, only the words, the tokens or lemmatized words, matter what the words are and the number of times they occur. Other techniques will look at the grammatical structure of the text and perhaps try to parse some or all of it. Yet others might use text embeddings. 7.3 Text embeddings and similarity. We have already mentioned word embeddings in the context of Word 2 C section 3.7, and the problem there was to determine whether two different words had the same or related meanings. But there is the similar, but more general, problem of determining the degree to which two entire text strings are related to, or similar to, each other. For example, one of these text strings might be a search or query string that a user has entered, and the other text string might be that of a complete document in a document collection. If these two are related, we might theorize that perhaps the document has some relevance to the search. Text embeddings are one technique to address text string similarity. There are many different ways of producing text embeddings, and there are many different free and commercial software applications to do it. For example, Cent2vec, FastText, Doc2vec, or GenSim. Almost all of them will produce a vector, i.e. a list, of numbers to represent the strings and also provide a measure that reveals how similar two vectors are. So, as an example, OpenAI's text embedding ADA-002 model embeds the string stochastic psittacosis to the vector. The source text strings can be of almost any length, although it would be usual to split up long texts into chunks. So, for example, a text document could be split into chunks, into chapters, pages, paragraphs, sentences, etc. Then vector for a search string could be matched into vectors for those chunks, and the relevant chunks have a location or locations within the document. There are some cautions. Modern embeddings can be produced by LLMs. Some LLMs have been trained on data produced or written before 2020. This means that such LLMs might not perform embedding well on more recent text involving recent events, slang, or changed practices of speaking or writing. Then, once you are in the world of LLMs, there might be bias. So, care is needed to check LLM embeddings for bias. There are tests to do this. Once there are vectors for strings and a similarity measure, several further opportunities become available. The context here is a corpus of text documents which has been embedded. Additional infrastructure would include a vector store, which is a database of the embedded vectors. 7.3.1 Searching by Meaning. We are all familiar with Find, the string-in-string search tool which is close to universal in word processing or text editing software. What this does is to find occurrences of the word, say attorney for example, in a document. But if attorney is the search string, it will not find lawyer, i.e. a synonym. But, in contrast, embeddings can search by meaning. They search by similarity of vectors. The vector for attorney, or for phrases in which it appears, will be similar to the vectors for phrases with lawyer in them. This is a very powerful addition to search. What it amounts to, roughly speaking, is search with thesaurus support built in. This, for example, allows for search by topic or subject matter. Also, similarity admits of degrees, so the results returned can be ranked by how similar they are to the query string. This is a type of ranking by relevance. 7.3.2 Research Trails. Once there is matching of chunks to chunks, then research problems or topics can be followed automatically from chunk to chunk, document to document, far and wide. This also might be useful outside of pure academic research. As examples, it might help with legal cases or with settling patent priority disputes. 7.3.3 Classification. Embedding can support classification in different ways. It can facilitate clustering. For example, the task of dividing a document corpus into 20, say, clusters of similar documents can be carried out by dividing the accompanying vector database into 20 clusters of similar vectors. It can facilitate classification using a supplied classification schema such as a thesaurus, controlled vocabulary, or ontological vocabulary. It could do this by seeing which vectors in the vector database of the texts were similar to the embedding vectors of the schema vocabulary. 7.3.41 Style of Recommendation. If some sample desirable documents are supplied from a user, a group of users, or from an institution such as a library, then embedding provides an easy way of finding other documents, i.e. recommendations, similar to the provided ones, and of ranking the recommendations. 7.3.5 Plagiarism Detection. The embedded vectors can reveal if two vectors are too similar, maybe even that they are identical. This perhaps would suggest that the one source is plagiarized from another. 7.4 Named Entity Recognition. Named Entity Recognition, NER, is the ability of the software or agent to recognize in a source text the references to particular entities, e.g. to London or to Sherlock Holmes or to the Korean War. NER can also usually classify the entities into people, places, institutions, etc. The references need not be in some canonical form. For example, one journal article might have the word London in it and another article the phrase the capital of England. These are two references to the same entity. NER using a large language model, such as BERT or a GPT-X, on news articles, research papers, social media posts, etc., is extremely accurate. As you would expect, it is not quite as good on new, or extremely rare, entities. However, it is plenty good enough for most applications, and it is distinctly better than humans attempting the same task. There is a difference here between the NLP model essentially recognizing or creating the relevant ontology and ontological vocabulary for itself against being provided with an ontology and controlled vocabulary to work with. For example, chemists have an ontology of elements and compounds, and NER could use that when analyzing research publications in chemistry. Accuracy is higher if the NER is provided with an ontology to use. NER is valuable for librarians as it allows a user to obtain, for example, all the articles on London in a collection. 7.5 Topic Modeling. Topic modeling can look at a text or collections of texts and determine their topics. Then it can tag those texts with their topics. There is a slightly older way of doing this, and a slightly newer way which would use LLMs and embeddings. With the older style, topic modeling is done by unsupervised learning. So, the ML software is clustering the contents of the texts. In the general case, it needs to be told how many clusters to make, and it does not have any names for those clusters. It needs to be guided as to those also. The result is that various different parts of the same text, or various different texts, can appear in the same cluster, meaning these parts or texts are on the same topic as each other. This type of analysis could also be done on documents, on paragraphs, on sentences, or on parts of sentences. To explain this at the level of documents, there are some background assumptions here, and some common techniques. The assumptions are A, that each document is a mixture of topics, B, that each topic is expressed using a certain vocabulary, i.e. using certain words, and C, that any word has a certain probability of belonging to the vocabulary for a specific topic. Then the calculation is merely a matter of counting the frequency of particular words, say the number of tokens of the word car, and seeing how the best clusters of words can be formed, doing justice to the word clusters and the documents. Common techniques include latent semantic analysis, LSA, latent semantic indexing, LSI, and latent Dirichlet allocation, LDA. The word latent here means hidden or in the background. See, for example, Manning, Raghavan, and Schutze 2009 for an explanation of these techniques. LDA can classify each document as a mixture of topics, Blay, Ng, and Jordan 2003. This type of analysis is very quick. So, the analyst can certainly experiment by varying the number of topics to find a result that is acceptable. Were modern-style embeddings to be used, the general approach would be similar, but the algorithms would use embedded vectors from a vector store. The main use cases of topic modeling are outside librarianship. As an example, security agencies may have an interest in which new threats are appearing in social media posts. Librarians, in their professional work, would typically have existing classification schemes that they would prefer to use. 7.6 Text Classification Problems. As we have explained under Section 7.2, certain kinds of text classification problems can be addressed using embeddings. But there are other techniques. There are a number of text classification problems that share a common ML approach. All that is needed are suitably labeled training data, produced in conjunction with the desired classification scheme, and then the ML system can classify the actual target data. 7.6.1 Shelving and Subject Classification. Text classification is similar to topic modeling, but it uses a supplied classification scheme. This means that the training of the ML system will be different. It will use supervised learning, and that means that there has to be labeled training data, which is always difficult to obtain. Modern systems are reasonably accurate. Classification, especially shelving classification, is something different to subject classification, indexing, or CV tagging. With books and DOI or LC, for example, a book can only have one slot. This is because it can have only one position on a shelf. This requires that the classification is exclusive and exhaustive and that each book carries only one, perhaps complex, tag, i.e. its call number. 7.6.2 Sentiment Analysis. Sentiment analysis, at its most basic, can pick out the emotive tone of some text. This might be useful in a commercial setting, for example, to process reviews of a product, dividing them into favorable, unfavorable, and indifferent. It typically works using only bag of words, i.e. the word tokens that appear in a document. It ignores what those words are saying. There are training data sets available for sentiment analysis. In that setting, supervised learning would be used to train an ML sentiment analyzer. You can see how a bag of words approach can go wrong with a naive analyzer. Say some example favorable words are good, brilliant, and excellent, and a text passage is written using negations only, e.g. the product is not good, not brilliant, and not excellent. The review is unfavorable, but naive sentiment analyzer might rate it as favorable because it contains only favorable words. Modern large language models, such as BERT and GPT-X, are very good at sentiment analysis. They would not use a bag of words approach. Also, they would not be trained using supervised learning. Likely they would be trained using self-supervision followed by reinforcement learning. Sentiment analysis might help librarians in any situation where they are trying to obtain feedback or opinions on items or policies or services or courses of action. The relevant patrons or constituents could be invited to provide their input, which then could be processed in whole or in part automatically using sentiment analysis. 7.6.3 Author or genre recognition. Most of the LLMs can work in one-shot or few-shots mode. The means that their user or programmer just needs to provide a few examples, and then the LLM will be able to carry out the task that is illustrated. In turn, this means that merely by providing some examples of an author's work or of books of a genre, and the LLM will be able to recognize which books are written by author or of which books are of which genre. 7.7 Controlled vocabularies, thesauri, and ontological vocabularies. ML/NLP can create controlled vocabularies, thesauri, ontologies, and ontological vocabularies for any corpus of text. It will be able to do so swiftly. Semi-algorithmic techniques for producing these kinds of vocabularies are well known. See, for example, Zhang 2005. In recent years, computer support would certainly have been used for these tasks. But natural language processing adds power tools. As a sketch of some of the techniques that might be involved. The terms in the documents can be clustered. This would be similar to topic modeling. These clusters can be arranged in hierarchies and favored labels attached to each cluster. That would produce a rudimentary thesaurus and controlled vocabulary, possibly latent semantic analysis, LSA, latent semantic indexing, LSI, and latent Dirichlet allocation, LDA, will be used. This will reveal the important concepts that are in use and their relations. There could be named entity recognition, picking out, for example, that London is the name of a thing or entity. There likely would be parts of speech, POS, tagging identifying nouns, verbs, noun phrases, etc. The results would be a thesauri or ontologies better than those produced without ML techniques, and produced quickly. Controlled vocabularies, and similar, are still important even with free text search and search by meaning. They can provide an interface, or commonality, between different documents or collections of documents. 7.8 Indexing and automatic indexing. A simple example of an index that we are all familiar with is that of an ordinary back-of-the-book index. The index itself consists of a list of entries. The entries are composed of headings and locators. For our purposes, we can assume the headings to constitute a controlled vocabulary, thesaurus, so there might be subheadings and subsubheadings, etc. in a hierarchical arrangement. Each entry is a pair of a thesaurus term and one or more locators. In the case of a book, a locator would just be a page number. So, the index itself has an easily navigable structure. The top-level terms are in alphabetical or filing order. But the book, insofar as its individual fine-grained topics are concerned, is a jumbled, disordered mess. Were a user to be interested in finding out where the ship Pequod is discussed, described, or alluded to in the novel Moby Dick, a proper index would make this task trivial, whereas doing it by looking through the book would be a considerable challenge. An index provides simple, readily understandable access to points of interest in an information mess. As to creating an index in the first place, Bella Haas-Weinberg writes, mainly under the assumption that the indexer is a human being.
An indexer must be something of a prophet envisioning the concepts likely to be sought by users of a document, expressing those concepts in terms likely to be sought by users, and providing cross-references from synonyms and alternative spellings as well as links to related terms to assist users in finding all the information that is relevant to their topics of interest. Weinberg, 2009.
Notice here that Weinberg refers to indexing in terms of concepts. It is possible to do derived indexing, which uses only terms that appear in the document or documents, or to do assigned indexing, which uses the concepts. Assigned indexing is superior, to assist users in finding all the information that is relevant to their topics of interest. Assigned indexing addresses the problem of synonyms and homographs, and also those very difficult cases where a concept is alluded to but not referred to explicitly. Derived indexing is pretty well trivial from a computing point of view. It is string and string searching. Assigned indexing is another matter entirely, as it seems to require understanding the material. Good indexing permits good retrieval. As the quote reveals, Weinberg sees the main intellectual challenge of indexing as being that of creating the controlled vocabulary thesaurus of headings that is to be employed. The secondary problem of scanning the text to catch all the locations for the locators in the entries is relatively routine and easy. Indexes can be surprisingly sophisticated. Indexes typically work on structured sources or across collections of sources. So, for example, an index for a book might tell you that material relating to the concept machine appears of page 37 and page 39. This is to conceive of the book as being a structured source, with pages which are themselves sources, and the index is finding the component sources. Or, as another example, an index across a digital collection of full-text sources might inform you that a particular topic is to be found within a few specific sources. In sum, indexes enable access to works within works, articles within periodicals, short stories, poems, or essays within a larger work, or individual papers from a conference. Cumulative indexes would use the same thesaurus to index across several different sources, for example, across all the monthly issues for a year's publication of a journal. AI/NLP can improve traditional indexing. It can do standard indexing faster than human indexers, and the result can be of higher quality. It can produce a headings thesaurus without difficulty. Then fleshing out the entries with the locators is essentially trivial. Many of the actual cases of indexing will use an antecedently provided thesaurus. For example, indexing medical journals would do this. The complete task then comes under the heading of automatic indexing. Another advantage to AI/NLP indexing is that it can provide locators to outside sources, for example to other books or texts with references to Pequod, the whaling ship in Moby Dick. Such pathways to wider resources are valuable for researchers. 7.9 Text abstracts, extracts, key phrases, keywords, and summaries. Abstracts usually either give the content in a shortened, sometimes structured, form, or point to or indicate what treasures are to be found in the work or works, but without actually providing those nuggets. Single sources can be abstracted, so too can multiple sources, as might be the case with abstracting the news from several different news sources into one abstract or abstracting many reviews of a source to produce an overall viewpoint. Prior to the 1950s, abstracting was always done by humans. But with the research of Lunn and others, attention was given to the possibilities of automatic abstraction, Lunn 1958. This work is a sub-area of computational linguistics. The techniques were certainly computational, and some may be classified as AI, but until very recently there was not really ML involved. Automation is important because there are many more documents that would benefit from being abstracted than there are human abstractors to do the work. Abstracting would generally be either abstractive summaries or extractive summaries. The former tries to understand what is in the source and then paraphrasing it in a shortened form. The latter extracts and condenses what is there, without necessarily understanding it, using statistical features and signposts. To illustrate the typical statistical features that might be used. Material at the beginning and end of the entire text is important. Material at the beginnings and ends of paragraphs is important. Words, other than stop words, i.e. the, etc., that appear frequently are important, and so on. Researchers in this area do have techniques for assessing their results. In some form or other, these are normally comparisons against abstracts that have been produced by humans. See, for example, Rouge i.e. Recall-Oriented Understudy for Gisting Evaluation, Lynn 2004. It seems fair to say, as of 2021, the computational abstracts are not of higher quality than human-authored ones. However, the software approach is thousands, millions, or billions of times faster than humans. So, for example, it can produce abstracts real-time, e.g., it can abstract news sources as fast as those sources are conveying news. There is machine learning in much of recent research on abstracting, but usually the ML is not used on its own, but rather is augmented by tried and true methods. Widyasari et al. 2020. There does not seem to be any technical problem as to why ML abstracting would just not get better and better. Likely NLP abstracting will be the equal of, or superior to, human abstracting sometime in the early 2020s. Producing key phrases or keywords is a similar, but simpler, problem to abstracting. If it is desired that the keys appear verbatim in the text, then challenge is like extractive summary. Often, though, it would prefer that keywords come from a controlled vocabulary, CV. If so, maybe none of a text's keywords actually appear in the text. For example, the non-CV word car might be in the text, but the preferred CV keyword term automobile is not. ML is a possibility both with extractive keywords and with pure abstractive keywords, e.g. controlled vocabulary keywords. Extractive keywords can be approached with unsupervised learning, Mishra 2021. This is a well-worked research area, not because the researchers are trying to help journal editors with lead-in keywords for articles. Rather, the computational linguists want to extract important words for further processing. Abstractive keywords, e.g. controlled vocabulary keywords, could be set up as a supervised classification problem. The CV would be the classes or categories, and the classification would note perhaps the best 8 terms that apply. These lead-ins specifically would help journal editors and researchers and librarians looking for documents. A summary of content would usually be longer and more detailed than an abstract of the same content. Summaries often rephrase the content. Otherwise, abstracts and summaries would be fairly similar. Summaries, or abstracts, may have specific features. They may have named entity recognition. If the source is fiction, a summary may contain a plot outline or an identification of the plot type or story type. Summarizing across multiple sources is also a form of synthesizing or aggregating those sources. Summarizing across 10 different articles on linear algebra amounts to one way of aggregating those articles. How might these techniques help librarianship? Summarizing documents may directly help users, which may be human or software, to find relevant content. Summaries may improve information access tools, such as catalogs and databases, by becoming part of the metadata that is used to characterize information resources. One of the first books written by machine learning lithium-ion batteries is a collective summary of 200 research articles, Writer 2019. 7.10 Text Mining and Question Answering. Text mining can extract potentially useful information from text, such as information regarding named entities, topics, classification features, genres, summaries, and sentiments of reviews, techniques that have been described in this chapter. Any or all of these types of information may help a user narrow an information search and thus make it more precise. Text mining is often used in conjunction with other techniques, for example, with sentiment analysis or with recommendation systems. Later we will look at undiscovered public knowledge, UPK, that is knowledge that is in books or libraries that is undiscovered. Text mining helps discover it. 7.11 Machine translation. This involves automatically translating text from one language to another. The value of this to librarianship is obvious. These topics and techniques are discussed elsewhere in this book. 7.12 Evidence. It has been asserted in this chapter that NLP is capable of doing this and that. Researchers in this field do have evidence. There are benchmarks that the systems are tested on, NLP Progress 2022. In fact, there is usually competition between the systems on how well they can do on the benchmarks. There are questions over the accuracy of the results of generative systems. There are difficulties with the prompts, with noise, context, and ambiguity. Also, an LLM will not usually predict the same thing twice thanks to the probabilities. So, it's not clear just what an accurate result is where an LLM is given the task of writing a paragraph in the style of Jane Austen. There is further discussion in section 4.8.1 on hallucinations. 7.13 This is not magic. Several of the topics and techniques mentioned in this chapter might sound a bit esoteric or far out. But, actually, the means for a programmer or library technical services department to produce suitable software is simple and readily available, now in 2023. The best approach would be to use large language models, LLMs, and to use one that has a public application programming interface, API. For example, OpenAI's GPT-4 does so. Then a programming environment like LangChain can be used to program or configure LLMs from their APIs. The resulting program to perform one of the tasks mentioned in this chapter might have about 50 lines of code in it. A professional programmer might write 7 lines of code a day when, as a prerequisite, they have to think about and research the problem. So, the first program might take a week to produce. But the second and subsequent ones could be written in about an hour each. Go to it.